Hello, so before we get started, I just want to thank Wamba and Dustin for your very kind comments on the last video, or the last VOD, I guess. It was not necessarily an easy stream to run, and I was feeling a little discouraged afterwards, and yeah, your comments were very helpful in undiscouraging me, so thank you. Of course, I'll never give up, but I might just feel discouraged, so but your comments help with that, so thank you very much, and let's start streaming. We're going to go through multi-sets today. Oh, by the way, I should address the church bells. There's church bells. They'll they'll be back. Don't worry. How are we connected? Are we connected well? What quality stream are we going to have today? I'm hoping on excellent. We got a bit rate. The bit rate's coming through. Excellent. Okay, let's get straight into this. Today we are going back to we're gonna go back to multi-sets. We're gonna do some exercises, and depending on how my brain feels today, which I think it should be reasonably good, we'll probably revisit the exercise from last time that I didn't do. I will tell you the story of that exercise. Didn't successfully complete. I'll tell you the story of that exercise when we get there, and I might just put a little notch in the video at that point. Hello, Bubbly Don. How are you doing? Doing homework. Very good. We've all got to do our homework. How's the homework going? What kind of homework is it? Let me see if I can remember anything today. Right. Trying to construct some spaces. Wow. You're like some sort of deity then if you can construct spaces. Maybe are they mathematical spaces, or are you constructing reality like in some sort of Marvel film? They call me the Demiurge. Well, that's good to know. Aha, mathematical spaces. Good. Reality can be whatever I want it to be on my paper. That's true. Paper is like that. Paper is a very holographic medium. Okay, how many 10-element multisets can be made from the symbols 1, 2, 3, and 4? Okay, so I guess so just trying to remember what we were on last week. Multiset is denoted. Well, we're being given a set, I suppose, and I think multisets are denoted with square brackets. Is that right? No. Yes. No. I think no. I think they're denoted in some other way. Let's find out how they're denoted. Those are lists. Oh, they are denoted with square brackets. Okay, good. And I guess we're allowed to have any number of these elements. So they can have unbounded, well, bounded, I suppose, by 10 multiplicity. Okay. So multiset, by the way, in case anyone watching later doesn't remember, I imagine you're familiar with this, Bobby Don. Is like a set, but you can have duplicates. So I guess when we're thinking about this, we could have. Oh, I need to get better at writing that. That is a S2. 1, 1, 1. We could have 10 ones basically. How many is that? Okay, some more. I think that's right. Okay, I don't know why I did that. Whoa, okay. Maybe my trackpad is being weird today. Anyway, okay, so we could have that, for example, which wouldn't be a valid set. Oh no, I've got it wrong again. Multi-set. Actually, the set is right here. Bobadon says, coincidentally, my spaces are made of lists that purposely exclude multiples. Because the theory becomes just so much more complicated if you have to keep track of collision data. It does sound like it. Sounds very advanced. I guess it's a thesis topic, so it would be. Okay, so there's a formula for this, I think. Or there's an approach. Let me see if I can remember what it was before I look back. So let's get rid of this stuff. So I think the approach we got given was this like stars and bars approach, where we have, in this case, how many bars we got? 4, I suppose. And we could have like everything, all the stars up to this point is the number of 1s we've got. All the stars between these two and the number of 2s we've got. All the numbers, all the stars here, and the star, by the way, it's nothing special, it's just the star symbol. 3, and then the 4s would be here, and I guess in reality we don't have anything here, so we don't actually need this bar. Right. Maybe we need it in the system, but I don't think we do. So this is supposed to lead us to some approach based on if we have 10 stars, well, let's just have 3. For example, we get to choose where we want to put the bars, maybe, like the indexes we want to put the bars. So I guess this would be index 0, 1, 2, 3. And so we get 4, choose, well, if we wanted just 1 bar, maybe 1. We'd end up with like 4 choose 1 possibilities for the first bar. I'm fairly sure I'm partially remembering this wrong. I'm gonna look back. I've done my retrieval practice. Let's just recover some of this material. Makes you wonder the actual time benefits in going through this last time, doesn't it? Okay. So where were we? Yeah. Okay, so here's the idea. Let's say we've got A, B, C, and D. And I think the question is, how many of cardinality 5? Now, we've got 4 elements and we have 3 bars, so I got that part right. And then we choose, what do we choose? Yeah, 8 choose 3. Now where does the 8 come from? Right, it's the total number of entries for 5 and 3, right. Choosing 3 of the 8 positions for the bars and filling the remaining positions with stars. Right, okay, so that's the idea. We end up with, let's say if it was like, well, in this case, let's say it's 4 symbols. Let's say we've got this A, B, C, D here. And we want to have, you know, the cardinality of whatever it is to be 5. I don't know why my hand is really slanting to the right today. Maybe I need to reorient my desk a little bit. I suppose it is somewhat difficult to move these things around as well. 4. Okay, let's try that. All right. Yeah, so in that case we have 8 slots. Whoa, terrible. Okay. Right. You'll notice these very faint guidelines on the board. Now, last time I was streaming, I was like, okay, we know your handwriting is terrible, but probably you can see your way to writing in a straight line. But it is also a weakness of mine. My hands are, you know, not, they don't like to obey my mind strictly, but most of my body doesn't either. So I put these lines here in an attempt to give myself some feedback and try to get myself writing more neatly, as it is annoying to not to write neatly. I imagine if you're taught mathematics formally, they're probably like, oh, your work is so messy, you know, you need to clean it up. And that is definitely a good idea, because if your work is messy, everything becomes more annoying to do. Okay, so yeah, so then we get to choose from these 8 slots. We get to choose, whoa, slow down. We get to choose 3 slots for the bars. So we've got 8 slots, 3 slots for the bars. And we could choose to put them here, 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 and that's all of them chosen. And then we have no choices left. We fill the rest with the stars. We haven't in this system said which symbols they're going. This took me a while to understand last time, actually. We haven't in our system so far chosen which symbols will go in which slots, but we don't need to. And the reason for that is that the bars encode that information. Everything before the first bar gets to be A. Everything after the first bar before the second bar gets to be our second symbol, B. Everything after the second bar before the third bar gets to be C, but we've got nothing there, so this doesn't get to put anywhere. And then everything after the third bar gets to be D. And so we end up with the sequence A, B, D, 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 which is of cardinality 5. It's a multi-set because it's got duplicates in it and is a, well, I suppose you could have a multi-set without duplicates, but this is a multi-set. And this is our thing made up of these 4 symbols with cardinality 5. Oh, you can't see any lines bullet on. That's so good. I was trying to work out if I needed a way to make the lines less visible, because ultimately they're only for me. But they're not visible because of compression. That's amazing. Oh, so good. That's even better than I expected. Still, they may show up on recording. Babylon says, this be much harder if the alphabet wasn't ordered. I guess that's true. Yeah, I admitted to the lines. I didn't even need to. Okay, so this is our approach for this example here. Now, for the exercise, it's the same exercise, just different numbers, right? So, in theory, we should be able to apply the same logic. Now, we've got 10 elements So let's call this, whoa, okay, let's call this B. Now the cardinality of B is going to be 10. And the symbols, I don't know what we'll call that. B, B. Can I do this yet? No, still looks terrible. The symbols are going to be 1, 2, 3, and 4. And so we're going to have the same number of bars, but we're going to have 10. No, we're going to have 3. We're going to have 13 slots because we need 3 bars to separate these elements, and then we need 10 actual symbols. So the answer is going to be... Hope you're enjoying these pigeons, by the way. This is the actual bird song, not the actual bird song, but very similar to the actual bird song that I experience every day in my real life. Okay, so this should be the answer, I think. Now, what is that numerically? Suppose I can show you this. May as well do some streaming for once. Well, you get the idea. Is it choose? No, it's math. What was it again? Comb. 10, choose... No, 13, choose 3. 286. Okay. That's number 1. Do I feel confident enough with this stuff to skip the even number ones? I don't think so. I think I'm just going to keep going. Why can't I write at all? Okay. Okay, number 2. How many 2-element multisets? 2-element multisets can be made from the 26 letters of the alphabet. So we still care about the number of slots, right? And in this case, we're going to have a lot of slots. We're going to have 28 slots. There are easier ways to do this, I think. But we're going to have 28 slots. Hello, Happy Nora. How are you doing? Good to see you. 28 slots. This feels inefficient, but 28 slots. And we're going to choose... No, wait. This is a funny inversion of the whole principle. We're going to have 28 slots. No, we're going to have 27 slots. No, yeah. It's so annoying that these numbers are so large. I don't want to draw them. Okay, so for number 1, we had 3 slots because we had 4 symbols, and we needed therefore 3 separating bars. Now for this one, we've got 26 slots. No, 26 symbols. But we're still going to need n-1, so we're going to need 25 bars. No. Yeah, 25 bars. Yeah, we're going to need 25 bars. So that's something we do know. Now the number of slots is going to be the number of bars, which is 25, plus the number of elements that we want, the number of stars we need to have. So that's 27. Now this number should, in theory, be relatively small, relatively, considering we're dealing with combinations and such. We might see large numbers and expect large results, but we're not going to get that. Because, like, let's say the number is going to be approximately 26 choices of the first letter and 26 choices of the second letter. But in fact, it might be exactly that. Yeah. Will we be double count? I don't think we'll be double counting. Anyway, let's find out. Okay, so the combinations answer is 351. And let's see if my intuition is right on 26 by 26. No, it's not. So this number is 676. So either my first answer is wrong or my intuition is wrong. Now, one thing, actually, we could have... No, wait, that doesn't work. We definitely have 26 choices on for the first character. And then we're definitely going to have 26 choices for the second character. I don't think they influence each other at all. So something's wrong here. Something's wrong in my mind, which makes me worry about this as well. Might just check. No, where? Have I made any silly mistakes anywhere? So, okay, Bobbledon's saying the discrepancy is in that AB is the same set as BA. Oh, of course. Yeah, I knew it was going to be duplicates somehow. I had a hunch it was going to be ordering somehow, but I was thinking too much like, well, A, we could get AA, and maybe there's like this would be a duplicate of like the other way around. But I was like, well, we're only going to get that once. But for some reason, I wasn't thinking A, B, which of course you're going to get if you choose A the first round and B the second round. That's an option if you do this method. If you choose B the first, you could choose B the first time and then A the second time, you get a distinct result. And so we're double counting this multiset because multisets do allow you to have duplicates, but they don't care about ordering, or rather multisets with different orderings are the same multiset, and so should not be double counted. So this double counts quite a bit. Thank you, Bobbledon. Yeah. So note that 26 times 26 is twice 351 minus 26. Yeah. So it's yeah, what's the other? Okay, this is good revision actually. Let me see if I can work out how to do this the other way. Okay. So we choose, it's choosing without replacement, right? So it's also 26, choose 2. Choices without replacement, right? I think I learned about this a different way at school than we've learned so far, so I'm still putting those two pieces together. So 26, choose 2 should be the right answer. 3, 2, 5 this time. Another answer. So that's not that's another intuition I've got that's wrong. Great. Well, that's still double. That was still double count, right? You're undercounting because you can't have. Oh yeah. Okay. Yeah. Yeah. Okay. So in this version of the picture, we then undercount because of this. Just Bubble. I'm just doing my homework now. In this version of the picture, we're undercounting because we're not counting a. So we avoid counting these two the same. We'll avoid double counting these, I think, but then we undercount these. So like if we were to add all those back in, which would be 26, choose 1, which is just going to be 26, right? We add these together. Let's see if I can, let me do some old school arithmetic just to keep myself in the, I do feel like it'd be better if I can do this mentally. 3, 2, 5. Here's where I embarrass myself terribly. Okay, 5 plus 6. Okay, all right. Here we go. Best stream on Twitch. All right, 11. Three, 5, 1. That's this. Okay. Okay, 3, 5, 1. That's good. I think that's also what Belinda was saying. Oh yeah, I could do yours, Bubbledon. Yeah, I'll just write your thesis. I'll write your thesis on stream. Has anyone done that? Write a thesis on stream before? And Belinda says, yeah, the fact you can add these together is exactly the Pascal's triangle property that the number below is the sum of the two above, because 27 choose 25 is 27 choose 2. Yeah, that makes sense. Yeah, because they'll be on the opposite side of the triangle, right? Those ones. Yeah. Okay. So yeah. So 25, 27. This is the 27th row, and we'll have 27 choose 1 and 27 choose 2, and then we'll have 27 choose 27, 27. No wait. No, we'll have 27 choose 0, 1, and 2, and then 27 choose 27, 26, and 25. So those will be the same. So that gives us this one. Now 27 choose 2 is also going to be okay, so 27 choose 25. Okay. I may stop doing this now. That's that's going to be 26 choose. You get the idea. Hand wave, hand wave. I believe you. You should stream it. Everyone should do more streaming. Streaming is like using AI, except it's not things that you tell anyone to do, and it's humans doing it instead of AI. So in a way, it's completely the opposite of AI. It doesn't do what you tell it to, and it's not a computer doing it. So instead of AI, just stream things. Okay. You have $1 in pennies. Of course, I mean, if you, I guess if you could use AI and stream as well. But you have $1 in pennies. Oh no. American currency. No, no. You have a dollar in pennies, a dollar in nickels, a dollar in dimes, and a dollar in quarters. What are you talking about? You give a friend, you give a friend 4 coins. How many ways can this be done? All right, what do we have? So we've got now a penny. That's 100, right? That's 100 of those makes $1. So we've got 100 pennies. Is that how you pluralize that? It is. Okay. Okay. Now nickels. Is that 5? If it's 5, then we have 25. Can anyone in the chat tell me what a nickel is? Nickels. 0.05. Okay, thank you. Thank you, Lorsair. No, that's not right. 25. 20. 20, because 20 times 5 is 100, right? Okay. Okay. How many, how much pre-decimalization coinage do I have? How many shillings are there? $1 in dimes. Now dimes, now a quarter is 25, so dimes got to be 10. So that means we're going to have 10 dimes and 4 quarters, right? For those of you who don't live in the UK or care about how the currency works, here we have pennies, two penny pieces. We just call them 2p, 5p, 10p, 25p, 50p, and that's it. I think there used to be a 30p, but you see how it's obvious from the name what that is? You see that? Thank you everyone. 2p did used to be tuppence, I guess, and there's the threepenny bit, I believe. Don't have that anymore. And there's the halfpenny, which is half a pence. Half, you see? You didn't even realize you go halves. The halfpenny, the 200 of those in a. Actually, no, I didn't. It actually used to be even different. I think there were halfpennies when we had decimal coinage. I'm not certain though, but there was also before this. We had pounds, shillings, and pence. A pound is 20 shillings, and 1 shilling is 12 pence. That's how it used to be, way back. And I say way back, it was 1971 when they changed it. So you'd have 20 times 12, 100, 240, 240 pence in a pound, rather than the 100 we have now. But we saw fit to move away from that system. It's not. I don't want to start anything here. Okay, so we got that. Now we have to look at the question. I give a friend 4 coins. How many ways can this be done? Okay, so if we want to do this, we've got 4 symbols, penny, nickel, dimes, and quarters, and they have some maximum multiplicities in here, which is also something that I can't remember how we did that from last week. but there'll be some way. I think maybe I'm just trying to guess now. I think maybe you could do this with like weird choosing, maybe. Anyway, let's look back, see if I can refresh my memory. Okay, so we got this, right? Permutations of banana. And yeah, okay, we've got, suppose a multiset A has n elements with the multiplicities of this sort, and the total number of permutations of A is, okay, fine. But this also puts a ceiling on, this puts a ceiling on the cardinality as well, which is a little bit awkward. Has anybody told us how to do that? Do we have to put together our own system for this? Maybe. It's kind of like this, maybe. A bag contains 20 identical red marbles, 3 green marbles, and blue marbles. You reach in and grab 20 marbles. There are many possible outcomes. This makes this, yeah. Yeah, this is not going to help us necessarily. How about this? The number of k element multiset, this is what we saw before, actually. The number of k element multisets that can be made from the elements of an n element set. Yeah. Okay, so we don't have anything obvious. No, actually, maybe we do. No, this is just permutations. This doesn't really help us. I don't think, because all of these are about permutations, and we've got a restriction here that we don't have elsewhere. Okay, so let's think about this more carefully. It's clearly not just a paint by numbers question. Okay, so right, dollar and pennies, dollar and nickels, dollar and dimes, dollar and quarters. You give a friend 4 coins. How many ways can this be done? So, first thing I'm thinking is, well, let's think about the slots maybe. So let's say we've got 4 slots and we want to pick, in fact, there's no actual restriction, which is kind of interesting. Because there's 4 coins, there's no time we're going to hit the maximum, right? We're never going to run out of any of these coins. So that's kind of useful to know. So if that were the case, then we could do this like, we could choose what this one is. We could choose what this one is. We could choose what this one is, but then we're going to have to be dealing with orderings. So we'd be over counting. because we could end up choosing like P, N, D, Q, and then we could choose P, D, N, Q, and then we'd end up with like this. We'd end up with the two equal multi-sets of coins, and we'd be double counting them. So we can't do that. Could we count the permutations and then snip off the end in some way? Yeah, I think that's right. Bubble it on. Could we think about snipping off the end and thinking about permutations of that? Or we were probably supposed to use stars and bars in this way. So maybe this restricts the number of stars that we have. That would be kind of interesting. So we could say then we've got 3 bars. In fact, let me put this slots. If this works, then we'll have 3 slots for the bars, and then 4 slots for the coins, and then we could choose the locations of each of the bars. So we could end up here, 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 and here. And then we'd fill in, let's say, no, that's too many. We'd fill in a penny, nickels would go here. Yeah, so we'd fit, no, actually, pennies would go here, nickels would go here, dimes would go here, and quarters would go here. So in that case, we'd have a nickel, a quarter, and a quarter. So we'd have the sequence N, Q, Q, Q. I think this would work, in which case the answer should be how many slots? 7 slots. 7 choose 3. I think. Let's not bother about solving that numerically. Let's say it's 7 choose 3. Yeah, 7 slots, which we choose, and we choose the place to have the bars, the 3 bars, and then we fill in, no, actually, no, we don't need to choose. Yeah, and then we fill in the rest with stars, and then we just deterministically put the coins at their place in the sequence. Okay. Great. Yeah, Happy Nora, you're right. It could be done so many extra ways. We really need to multiply this by something like mood. Style. The set of possible stars is expanding as we speak. Okay, wow. Need to improve the speed over that. Right. 4. You know, we've got some new baby pigeons around where I live. They've arrived. Nobody docks me based on the pigeon network. We saw them the other day, and then a magpie scared them off. These are the things that excite me in my life. A bag contains 20 identical red balls, 20 identical blue balls, 20 identical green balls, and 20 identical white balls. Who would do that? Why are you going to mix all those balls up? You reach in and grab 15 balls. How many different outcomes are possible? Okay, once again, we're not going to saturate any of the collections. So we'd end up with how many slots? We'd end up with 15 slots plus 3 separators because we've got 4 different item types. So the answer is going to be 18. 18. Choose 3. 3. M&Ms. True, I guess. Be cool to have spherical M&Ms. We do have M&Ms here, but we also have Smarties. They are different in some way. One of the notable things about Smarties is that they come in a special cardboard tube, which has a little flip-up cap, which I think is a far better delivery mechanism for a gorgeable food. The tube is very important. I also think they may be slightly bigger Smarties. Yeah, the tube's very important. Yeah, we also do have M&M World. Is that what they call it? M&M Land? There's an M&M place, an M&M zone in London, and possibly other places as well. But there is no Smarties World, to my knowledge. That's not Smarties style. It's not so... It's not... Smarties aren't really as tacky. You know, none of the Smarties have personalities. They're not a hot Smartie. That would be horrible. They're all just chocolates. They're not real. They're not characters. I also learned in a video recently that like Mars, the Mars company, who I believe make M&Ms, they came out of like a family feud. It's kind of a cool video. If I can remember what it was called or who made it, I would tell you. You've been to M&M World, Bubbledon. Wow. What was it like? Did you get to meet the hot M&M? Did they let you meet her? I guess any of them could be hot, really. If you maybe you don't like the hot M&M. Is it green? Sorry, she green? The hot M&M? Yeah. I guess you know, it could be like K-pop. There's one for everyone. You know, is that how K-pop works? I guess I'm just superimposing the band culture that I know about. Yellow M&M is your bias. Okay. One day I will learn to write. Let me see the best circle I can do. Let me try it. Oh, that's so bad. Surely not. Surely I can do better than that. There must be something going on that makes my circles so bad. I think there is. See, that's not... I think there's something going on with my mapping between coordinate systems in this app. Yeah, there definitely is. Yeah, I think there's some mapping that's gone wrong. Yeah, I need to get like some shapes and draw around them and then just see what I'm actually drawing. Acyclasia. Huh. Yeah, could be. Inability to draw a circle. Could be. All right, 5. Not the balls question again. 20 identical red balls, 20 identical blue balls, 20 identical green balls, and 1 white ball. You reach in and grab 15 balls. How many different outcomes are possible? Now this is different because we are going to saturate the white ball if we choose it at all. So if we did that, if, like let's say we came up with another system. No, that won't work. That won't work. I was trying to think if you could like select the position of the white ball or something, but that certainly wouldn't work simplistically. Let's say if we have let's simplify this and think about, I don't know, two red, two blue, and two green, and one white. And let's say we want to have like we pick out two balls. Now in this case, let's say if we wanted our bar approach, we need 3 bars and 2 slots, so we're going to need 5 spaces. And we could pick like one bar here and 1 bar here, and then everything here would be, let's say we weren't worrying about the restriction right now, everything here would be red, everything here would be blue. Oh no, we need 3 bars, don't we? Everything here would be green, and everything here would be white. But let's pick differently. Let's say we have this, this, and then we're going to end up choosing 2 whites, which is not allowed. So we need some way to restrict maybe the position of this bar. Maybe we could say, just for making it slightly easier to deal with, we could say the white bar is the first, the white element comes first. Now if we did that, we could say that the white bar can be in either this position or this position. It can be there, in which case we get 0 white balls, or it can be here, in which case we get 1 white ball. Now, then we have a bit of a problem with the rest of the bars, I think. So let's say if we go here, then this bar ends up being kind of special. Not like the others, and its position affects the possible positions of the other bars. So if the white bar is here, then the other bar can go, like let's say the red bar can go here, and we're essentially choosing, like this is, I don't know, 2 choose 1, and then everything from, in fact, everything from this point on we end up choosing 4 choose 2. But if we have the white bar go here, oops, if the other white bar go here, then it has to be 3, choose 3. No, choose 2. 2 bars. They're telling me that acyclasia is not real. They're saying it's not real in the chat. Okay, so I mean that's unfortunate, but like in theory it works. The issue then is we have to do this like way more times. Well, no, actually we don't. One white ball is okay. One white ball is okay. If we end up having like more complex problems later on, we run out of, like, this solution becomes annoying to scale quite quickly. Doesn't necessarily mean it won't work, just I won't really feel like, I will feel like there should be an easier solution. Okay, so another way of looking at this is, let's say we're going to have all the possibilities for where there's no white ball, and all the possibilities for where there's one white ball, and that's going to be it's just going to be a doubling, right? In this case, just going to be a doubling. No, it's not, because actually it will affect the possibilities. And then we have, what is it? We've got 20 red. No, wait. 20 red, 20 blue, 20 green. And if we've got 0 white balls, we need to choose 15 of those, in which case we've got 15, 16, 17, because 2 bars left. 17, choose 2 different possibilities. If we do this, we do have the white ball. We're actually only going to be choosing 14 more balls, which means we're going to have 16, choose 2. And so the result is probably going to be 17, choose 2, plus 16, choose 2. Hi, F going. We are solving 5. Thanks for asking. I need a better indicator for that. You're right. Okay. So let's look at this numerically just to see if this actually makes any sense. 17, choose 2, plus 16, choose 2. 2, 5, 6 seems oddly round, but it doesn't mean it's wrong. Doesn't seem wrong as a number. It's not giving me wrong vibes. So let's go with it. I don't think I'm going to be able to get my brain to do more, and the answer will correct me, and we will find out. Okay. Question 6. A bag contains 20 identical red balls, blue balls, and green balls, 1 white ball and 1 black ball. You reach in and grab 20 balls. How many different outcomes are possible? So it's kind of a scaling up of the last question. Now, in that case, we would have the case in which we have 0 white, and then we'd have 0 black, 1 black, 1 white, and then 1 black, sorry, 0 blacks. I don't know why I have to put 0 on the top. I guess it makes sense. 0 black and 1 white. This seems calculable. Now, in this case, we've got to choose 15. Yeah, we've got no additional balls, so 15. 15 choose 1, 2, 3, 2. So we've got 2 borders to choose. Then here we've got 14. No, wait. 17, because of the bars. Yeah, then it's 16. Choose 2. We're not talking about blue balls on the stream. We're not getting into that. 16, choose 2 here as well. And then 15, because we've got 13 and then 2 bars. 15, choose 2. Okay. And so that would be the sum of some of these. Let's say. I don't know how to use that symbol. Add them all up. Thanks, Howling AF. It is, I feel good. I generally feel good. I generally feel good about doing my homework. I guess that was imbued in me. How are you doing, Howling AF? So that's 481. I mean, kind of in the region of making sense. This is doing this on my own. Essentially, the project here is I'm trying to work through all of The Art of Computer Programming by Donald Knuth. Probably not do all the exercises because some are like research level, but generally study all of it. But from the position of a relatively ordinary, unmathematically trained mind, like I can write code. I've been a software engineer for a while. I'm reasonably competent there, but I'm not a computer scientist. So, you know, what will it take to work through all of that? One of the things it will take to work through all of those books is better mathematical competency that I currently have. And so after the first chapter, I think we started working through the book of proof in order to learn how to prove things, because proofs come up in the book. And I'd like to be able to understand what Donald Knuth is talking about. So we're now working through these, which is also prerequisite within the book of proof in order to then do that. All indeed, yeah, all of the volumes, as many as he gets done. Let's say he's 80 something now, so I don't think he'll probably finish it. Going through one of them, well, that's going to be about, you know, it's going to be some fraction as difficult. You should do it. You should definitely do it. And if you know, I will be streaming and uploading VODs of this process for as long as it takes. So at some point there should be videos. I don't know if they'll necessarily explain what's going on, but may help with accessing them as well. Yeah, the hardest deadline of all, that is true. Yeah. Yeah, and the one that, well, I suppose it can be pushed back, but even that comes with some sacrifices. 7. In how many ways can you place 20 identical balls into 5 different boxes? sort of an interesting alternative way of putting it. Because then you just think about like dividers, right? So let's say it was one big box. Is this related to pigeons? Maybe. We'll find out. Whoa. Let's say we had this and then we divide it into sufficiently shaped, like we get to choose where we put the dividers so that we can fit 20 balls into them. So we could put them here and here and here, and then we end up with 1, 2, 3, okay, 4, 5. So we need 4 dividers, which is kind of comparable logic to our slots, right? In our stars and bars diagrams. Have I already run into anything that I wish I'd done differently? Good question. No, I don't think so. I don't think so, actually. Like, obviously, as you learn, you realize that you've made mistakes previously. And for those of you who weren't there at the start, the question which I bashed my head against last session and was unsuccessful in solving, I will try that again today towards the end. I stared at it for some time but did not do any work, but I did stare at it. So we will see whether my new approach will work or whether I'll have that problem to go on with. But learning's just hard, right? Like there's no way really around it. Yeah, no regrets because I chose this way. Yeah, I don't know actually. I will get to the point where I wish I did things differently, but I'm actually not sure I am there yet. It's a good question though. If anybody watches this video in like a year, ask me again. Yeah. Let's hope Donald Knuth has the special genes. Okay, Howling asks, are you just going through it front to back, or do you skip topics you're not as interested in? I haven't set myself any like big rules yet, but I'm a bit of a completionist by temperament. So unless I really I think so there are a lot of exercises, right, in those books. And the exercises, I don't think I'm going to be able to do a lot of them the first time round, but I think by the time I've worked through more material, I probably will be able to come back to them. And so I probably will go back to some. But I'm probably not going to skip things just because I'm not interested in them. Because I'm also a content creator, and I also have a bit of a project to try to spend time with the great works of our field. Our field is, who knows what's going to happen to our field exactly, but there are already some great works. Donald Knuth's The Art of Computer Programming, I believe to be one of them, and I think it's worth studying, even the parts that are not immediately interesting, because it's interesting to think about why he put them in there, and maybe even if they're boring or not obviously important anymore, or some of the people who come in here, they say an AI could one-shot this. Even if all that's true, there could be something inside that material which could be very interesting and valuable. And these books are so, I don't want to say underread, but they're not. They sit on shelves more than they are read. And I want to unlock some of that for myself, but also for other people. And there are ideas in there and probably stories in there and things in there which I'd like to bring to a wider audience, because the guy spent his whole life, I mean, he did other things obviously, but he spent his whole life writing these books. And there's there could be some amazing things in there that, yeah, I just want to find them for myself and also for other people. Yeah. Hi, Namir. How you doing? I'll put it on. You're reading an old paper by Poincare. I'm pronouncing that wrong, I know. Poincare? I don't know. Yeah, people are just inventing stuff all the time. It's wild, and it's wild how arbitrary some of it is. I think there's a general idea, I think, which is kind of a bit of a dismal idea, that things exist in the world basically because they're inevitable. It's just that, such and such happened to be in the right place at the right time. If they weren't, it would have been somebody else. And I think that sometimes makes people feel like they have nothing to contribute. Like, if I'm not in the right place, if I don't happen to do anything like that, if I don't, somebody else will do it. But I don't think that's, I have a hunch anyway. I believe that's not true. I think there are a lot of ways in which things are just the way they are because the person, like, somebody chose for them to be that way. And they created something which lasted. And I'm thinking about this particular moment because I'm working on another project, which is to do with the history of the spreadsheet, which I think is, we owe so much to the team that created that. And there's the idea that the spreadsheet was just inevitable, like people were just doing this, and it was a digitization project. People were building the spreadsheet. People were doing Oh yeah, okay. By the way, there's church bells in this audio that come back. Yeah, that the spreadsheet was like a normal, like people were doing analog spreadsheets and they just digitized them, and that's what the spreadsheet was about. It didn't really matter any of the work anyone did because it was going to happen anyway. But I really think it wasn't. I think the spreadsheet is like kind of a remarkable piece of user interface design that is still basically the same set of ideas as Dan Bricklin had all the way back. And I think if he hadn't done that, we'd be using quite a different piece of software today, and we might not even have a recognizable spreadsheet. Anyway, spreadsheet, etc. I guess it is on the hour. That's wild. I don't think the recording's an hour long, although it would be cool if it was. Keyskiller 0. What's my reading setup? So, glad you asked. Glad you asked. Because it's I iterated every time. So, what I have... I'm going to switch to OBS. I'm currently using like Meld. I think just kind of makes me feel nicer and less like I'm using OBS. I have over here, this zone, I've got a PDF in the preview app on macOS. This is being screen captured by the OBS like software I'm using. It is then being keyed to remove the background for some reason. I don't know, might want something underneath it. And it's being inverted. So we then have, instead of it being white, it's like got my background and it's got white text. Now, the note taking, this is custom built. So what I have is I have an app. It uses a library called Perfect Freehand by the founder of TLDraw, Steve Riz. But it's so TLDraw and Perfect Freehand, they work based on SVG, and so it's essentially an SVG drawing, which therefore has a transparent background. This is then a browser source in the OBS-like thing I'm using. So it's a transparent browser source. Over the top goes, so I can even draw on my own, my own face if I want to do this. So this browser source synchronizes from a server which has, all of this in it. Now, I don't like drawing with my mouse, although I have done it. So as a result, I also have an iPad. The iPad is also loading a slightly modified version of the note-taking software, which just controls this little red pointer. And the wild thing is one of the things that if you want to have like a graphics tablet style interface where you want to look at the screen, you don't want to look at you have your head down here looking at this, you want to look at the screen, you need to be able to see the cursor. And the way that Apple Pencil typically works is you draw and it draws a line. But I don't like that because I need to see the cursor so I know where I'm going to draw. So instead, I have another browser window open, which is taking my keyboard input. When I hold down the grave quote type symbol, it draws. And when I'm not holding it down, it doesn't. When I'm holding down space, it moves it. When I'm holding down E, it erases it. So we've got a kind of control panel on the left, iPad on the right. All goes through to this. Yeah. Anyway, but you're good asking now. But yeah, and then I can just scroll this around, and I can make notes, but the notes don't scroll or anything. Or I can make them scroll, but I can only make them scroll in a different interface. So yeah, like just fiddle around. Yeah, I'm operating the space shuttle basically. I love a complex. One of the great things about building your own tools is you can build interfaces incrementally to fit the way you are learning how to use them, which is just something you can't get with pre-built software. But if you build custom-built software, you can build it to work just like you want it to. You can even build features that no user outside of yourself would ever tolerate, because for you it feels like it's like nobody would ever want to use this apart from me. But because it's me, I'm designing for my own favorite user, me. Yeah. Naomi, you're excited for the World Cup start. Who are you supporting? Who are you supporting? I want to know this. I want to know who everyone's supporting. And then I'll tell you who I'm supporting. I'm well, thank you. Thank you for asking. I'm pretty good. OBS was created by a really cool person, says Happy Noel. Wow. I don't know who created it. Cool person. I'll have to look that up so I know more about what you're saying. Blue cursor, I got rid of the blue cursor. I get to see the blue cursor, but you don't now. So I'm moving it around, but you don't get to see it. I don't have a good purpose for it yet, but maybe someday I will. Those of you may have missed the fact that there are very faint grey lines to keep me writing neatly on this, but I don't think you can see them because of the compression, which is good. Okay. Kip says, I find it weird how people are now biased towards new technology and just assume that newer is better and that there are no trade-offs like the cloud and AI. But with programming, I feel like people are relying on frameworks and abstraction that causes the end result code to be inefficient. But people, including me, aren't being taught lower-level languages, logical foundations, etc. that would be needed. I had a really interesting conversation with someone today. Somebody, I think I can share this. Somebody from the organization Code Your Future in the UK. They work with I think refugees, amongst others, to enter the software engineering field. Of course, it's a tough job at the moment. And we were talking about how potentially theory is going to become even more important, because it used to be like your primary skill really was fluent programming. Like it was a language skill. Like, right, your job is building software, you need to be fluent in the code necessary to build software, but that is no longer really true. Like, you don't, like it like it's a very valuable skill. I still like it, I still think it's important, but you can get by quite far without writing code yourself and being fluent in it. But the theory is still very, very important. The theory being able to understand code, the theory of how code works and how it performs and how it can be structured, that's still really important if you're going to be able to steer these systems appropriately and get them working as they should do, debugging even. So maybe we could, because we know we need to train new people, and right now it's not necessarily obvious, but employers are particularly interested in doing that. Maybe we will be seeing people trained a lot more in the theory and less in the practical, or at least the practical as we knew it. So we'll be spending more time on computer architecture, more time on the structure of code, more time on programming languages, more time on computer science, maybe less time on building software from manually, which of all the possible futures we could be going into, it's not the one I hate the most. Like, the theory of software engineering is interesting and valuable, and maybe more time spent on that could be good. Certainly interesting and good for my stream if we're doing all this. Happy Norris says, no blue cursor, unwatchable. Yeah, true, actually. True, sorry. Next time. How many hype? Hello. Name is supporting Spain. Ah, cool. I hear they're pretty favored. Anyone else in this chat of potential non-soccer / football supporters got a team they're supporting? Hey, LTS Austin, hello. It would be a nice outcome actually if people spent more time in the theory. I found a crazy thing. Save to watch later. All right, that's how I know it's a legit link. I'll save it. Where am I going to save it? I'm going to take a photo of it. That's what I'll do. Come on. Gosh, software, huh? Vectors. Of course I'm into vectors. I love it. I see there's a new 2Swap collab with Veritasium. Now there's going to be a spicy video. Anyone watch that one? I'm excited to watch that one. Get that VC money, 2Swap. We want to see that. We want to see that video. I would love to see 2Swap getting funded. Yeah, but I haven't watched it yet. And there's a new 3 Blue and Brown as well on Claude Shannon. Gosh, I wish I got there first. I mean, not that I would do anything like he did, but I need to cover Claude Shannon. Need to cover so much stuff. Oh my gosh. I don't think 2Swap has been bought by private equity, but if I was a private equity firm and I owned Veritasium, and I think that's the story. That's what happened. That's what's happening now. Then I would. Well, I mean, I'm sure it's not the VC firm making the shots, but basically, 2Swap has done a collaboration with Veritasium on, I think, Google Maps. I've not watched it yet, but I should imagine, as a result of Veritasium having some backing, maybe it's just cool that 2Swap, because I think of 2Swap not as like a small creator exactly, but hasn't done like so many videos, really nice videos. You not watched 2Swap yet, and you like software, and you like algorithms, just. It's great stuff. Like it's really good. I just love to see 2Swap succeeding basically, and if it takes VC money to do that, I'm totally happy with that. Kiskilla says, what do you recommend as sources for beginners to intermediate devs? Can't tackle Advent of Code, I guess. Yes, yet. Yeah, good question. Beginner to intermediate devs at low level. Yeah, I'd be curious to know if anyone has anything in the chat. There's the obvious ones. I've not worked through them, like Nan to Tetris and such. I have a couple of videos around assembly, which I think are okay as introductory videos. Assembly, probably the main thing I would suggest for assembly is assembly is really simple, kind of. Like, assembly is a bit like trying to build a car with only like single atoms. So, I mean, let's say atoms are simple for a moment. Let's say that. Let's say you have very simple building blocks in assembly, but it takes, because they're so small and so simple and in theory so easy to understand in isolation, like it's quite a lot of work to produce something, which makes it kind of rewarding for a learner because it's kind of relatively simple to understand if you can understand the basics of registers and instructions and get the tooling working, most of which is in my video about assembly. Then like you can kind of work towards the bigger stuff. Now, most people don't want to build anything bigger with assembly, and there's good reasons for that. But yeah, I would also recommend, in fact, there is something I'd recommend. Oh, you're more into algorithms and math. Yeah, I don't have that many recommendations for that. Wow, I really should answer these questions better. Thank you for the questions. I don't think I have any good answers. I was going to recommend. There's a tool that I linked to in my assembly video, which is called Ketman. Way old, real old tool, but a really nice tutorial in assembly. Yeah. But so much of this is just getting it together and doing it. Nanta Tetris is 120 videos playlist. Oh my gosh. Wow. I didn't even know that. You know, Keyskiller, you could just read The Art of Computer Programming. I know it's kind of cliched recommendation considering the project here, but yeah, you could just read The Art of Computer Programming. If you're more interested in the algorithms and math side, you could just read The Art of Computer Programming. You won't be able to follow all of it straight off. If you have a mathematical background, you probably will be able to follow all of it straight off better than I can. I think somebody else in this group is doing that, but I can't quite remember who it is. I apologize. Please make yourself known if you do, if that is you. Should I pursue calculus and linear algebra before? Depends what you want to do. If you're into computer science, those do seem like useful prerequisites. If you want to make software, probably not necessary. Oh yeah, Ben Eater. Yeah, has he stopped uploading? Ben Eater's great. Yeah, in fact, I would recommend Ben Eater's videos to anyone. I would especially recommend them if you have access to a lab with all of the components involved. So much of the difference between, you could actually do a really bad course, but engage with all of the exercises very deeply, and get much better learning than doing a really good course and engaging with the exercises really poorly. It's a sad truth, but that is the reality of it. Okay, question 7. In how many ways can you place 20 identical balls into 5 different boxes? So, let's say one way we can think about this is as a stars and bars diagram again. We have, let's say, however many slots, and we put 4 dividers down. Let's say here, and then whatever. And then we just fill the rest with balls, right? So I think in this case, this will be 24. Choose 4. I'm just trying to work out if there's something funny about boxes. I don't think there's any difference between one box with 4 dividers and 5 different boxes. Yeah, I think that's okay. Okay, do we want to speed up a little bit here? I'm going to try doing the odd questions from here on. Harmony Hype, hello. How many streams did I miss? Last stream I watched was about combinatorics. Combinatorics? We're still there. We're still combinatorics. We're learning about multisets. So we're counting multisets right now. So I don't... You may have missed 1 or 2 streams. Not millions, though. Recommendation from Laurie Wired. Well, you got to follow that one. Yeah, I haven't watched her latest video yet. Has anyone else? I really should. Laurie Wired is great. Laurie Wired... Laurie Wired is great. Laurie Wired is like someone who makes me like jealous. That's how good Laurie Wired is. Okay. 9. A bag contains 50 pennies, 50 nickels. This again. You reach in and grab 30 coins. How many different outcomes are possible? Okay, we don't care about the value of them this time. That's good. So we've basically got 4 symbols. We're not going to saturate them, so that's fine. We're going to grab 30 coins. So we're going to end up... Am I going to just get tripped up by some of these questions? Okay, so we've got 30 coins and 3 dividers. Because we've got 4 types. So it's 33. Choose 3. I think that's right. And then 11. How many? How many integer solutions does the equation w plus x plus y plus z equals 100? Nobody going to tell me about who they're supporting in the World Cup then, apart from Neymar. And Doka 2020 queries, is it the aesthetics of Laurie Wired that I like? No. I think if I was to sum up the thing that I'm jealous of Laurie Wired for, it is success. She's just very successful. She's I mean, I'm sure I'm not trying to denigrate her at all. Like, success comes from hard work, right? And you can sort of follow the journey of her channel and the production values. I think there was a moment in which she really invested in it, and like it does feel like the production values on her channel are really good. The content is well focused, and I think she's been rewarded for that. Yeah, I actually think there was one time I needed actually to use... They're going to need to use some of her software for something. Yeah, anyway. The aesthetics are good, but they're actually... yeah. That's definitely not the major thing. I think she's doing some good storytelling at the moment as well. There is sometimes a little bit of... there's a little bit of the... you ever seen this? Whoa, okay. Circle. Why am I forcing myself to draw circles? You know. There's a little bit of the monomyth about some of the storytelling. I mean, who can criticize that, right? The monomyth is important. If you don't know what the monomyth is and you're like, what on earth is K drawing. Look that up. Basically, it's like a storytelling structure. If you ever watched a Corridor Crew video, they follow it like to the T. And the thing you notice is in a monomyth style storytelling, you end up with like the moment of despair, the trough of despair. Wow. One day I'll be able to write the trough of despair, where it seems like our hero will not accomplish their goal, but then everything changes, you know, and you know, then I remembered, oh, it's this, and then everything was great. You know, there's a little bit of that, but you know, it's just because I've seen a lot of it, but she is very good. Yeah, she's very good. I would like to emulate, obviously not exactly what she does, but I admire what she does. Hero's Journey, indeed. Yeah. Yeah, it's called the monomyth sometimes also, I think, in the book, because it's like the one story. Like that's the argument. There's only, you know, every story is kind of structured around that. I think that's why it's called the monomyth anyway. Maybe wrong, I never read the book. But indeed, the hero's journey. The hero's journey is great, but it is getting a bit, YouTube is getting a bit saturated with the hero's journey, I think, at the moment. And again, I do love Corridor Crew. I am a subscriber even. I love the videos, but the monomyth comes through in everyone really obviously. No, Happy Nora, no. Okay, I'll bring the blue cursor back next time. Next time I'll bring it back. What book? What book? Now that's a good question. Somebody's challenging my somebody's challenging my credentials. Joseph Campbell's The Hero with a Thousand Faces. I think he refers to it as the monomyth in there. But the idea of the hero's journey, I believe, like the observation that the hero's journey exists, I believe comes out of the book by Joseph Campbell. But it's obviously not his idea because it's existed throughout history, right? Or throughout storytelling. And speaking of which, then I will go back to some work. If you have not read / experienced the Odyssey by the lyric poet, I guess, Homer, highly recommend it. I know it's an old take. It's one of the oldest takes, but it goes hard. Like, it's great. The Odyssey is great. And if you don't like reading ancient poetry, I guess it is an ancient classical poetry. Anyway, there is a great retelling on YouTube at the moment, which is just so good. It's just like feels incredibly modern, and the reason for that is that storytelling has a particular structure. I don't know if I guess the Odyssey is not exactly the monomyth. It's like a few monomyths, but it's just such a good story. Odyssey movie coming this year. Is it by Christopher Nolan? Really? You're telling me this for the first time? Really? Oh, man. Oh, wow. Okay, the YouTube video version of the Odyssey is like, it's like max 4 hours. It's like one of the founding pieces of Western literature, and there's a reason. Like, it is good. It is good. Like, listen to the first 15 minutes, and if you're not hooked, turn it off. But like, it's, oh wow, it's so good. It's so good. Seriously, brah, it is so good. Okay, anyway. Just glazing Homer here. Okay. Well, okay, got it. Really, is Chris Nolan really making the Odyssey? Is this true? I'm not even going to Google it because I would like me to. I don't. That's wild. Is he doing the Iliad? Is it called the Iliad? I've not actually gone through the Iliad, though it's on my list now. Pretty cool. I guess, I mean, to be fair, like one of the first things I thought about the Odyssey is it feels so modern. Like it feels like a Netflix series, like in the best possible way. Like, and the cool thing is you're you know, sometimes you like into like a genre of music and then you listen to a band that everyone is like crazy about, and then it seems like, wow, I've heard this before. And the reason you've heard it before is because that was the band or one of the bands that made that genre happen because it was so good. Well, the Odyssey is like that, but it still holds up. Okay, I'll find the Odyssey video. I'll find it. I've mentioned it before, I think, but oh, all right, where is it? Oh no, Christopher Nolan's outcompeted it. Okay, I gotta go deeper. Totally, Kip. So those of you who don't know, Kip is 100% right. So Homer was he didn't, as far as we know, he didn't write it down, right? So the story goes, Homer, this is not the story but the backstory, like, the is he's blind, right? Homer is blind lyric poet, and he comes up with these stories and he just tells them, like he tells the stories. And there was the tradition of, you remember, you teach someone the poetry and they remember it and then they recite it. And this, so the version we have of the Odyssey is probably from hundreds of years after Homer lived, because they'd been remembering it and retelling it and retelling it and retelling it. And so in the process, in theory, in the process of retelling it, it possibly gets embellished or changed, or some of the rough edges get smoothed out as well. So it's not just Homer's work, it's also the work of all the people who retold it and kind of worked on it, I suppose, as time went on. And there are different versions of it, I think, that we have now. And yeah, I mean, it's probably the work of many generations of people. So no wonder it's good, right? Imagine if you had to like watch all the Marvel movies and remember them and then tell them to your children, and then their children would have to tell them to their children, and then their children have to tell them to their children. Probably after like a few hundred years, you might end up with a few good movies out of that, right? Okay, here's the video. That's the video. It's not like the story is special. The video is good. I mean, I think it's a good retelling. I mean, I don't know because I've not read the original lyric poetry, but and I probably wouldn't. But just because, again, it's like hard. It's kind of probably a bit inaccessible now, but they've kind of modernized it enough for it to feel like a kind of a legible story. And yeah, it's great. Stick it on. Yeah, Ndeka's saying, I like this. This is, I've been nerd smart by this. I like Iliad because it's less like the hero journey. The Odyssey is more like a modern story. So there's actually a whole book, I think, in part written about that fact. So yeah, the Iliad is the story of like a particular, I think, a particular siege or battle related to some classical cities. And the Odyssey is, it sounds wild, right? So the story of the Odyssey, let's say this has been this big battle. I think the main character is called Odysseus, I think. Don't quote me on that. I don't remember names very well. Big battle. Odysseus is like the leader or something. And the film story number 1, the Iliad, is all about the battle. Story number 2 is about Odysseus's journey home. It's just about his journey home. That's it. Yeah, so it like that, I mean, that by itself, and this is like a work of like literature that persists to this day. It's just about his time home, his going home, and all the different things he encounters on the way. Yeah, and anyway, so the Iliad and the Odyssey, they're different, quite different in style. It's observed by another book, a psychology book, which is like a really weird book called. Does anyone know what I'm about to say? This is a bit from memory. Let me see if I can. Yeah, it's by Julian Jaynes, I think. The Origin of Consciousness in the Breakdown of the Bicameral Mind. And like, I'm really summarizing now, but I think basically Jaynes' idea is that human beings were not conscious until a certain point in history. Before this, they were basically like ping pong balls, just bouncing around. You know, things happen, react, but you don't have consciousness in the same way we have now. And then at a certain point, we developed consciousness in order to cope with a change in civilization at that time. And I think he locates, like, he explores this transition from not conscious, like before the bicameral. No. Anyway, he explores this transition through the difference between the Iliad and the Odyssey. So there's that as well. there's that as well. So maybe, yeah. Anyway, if you're interested in that, also cool. Have I heard a theory where psychedelic substance use could be a way we gain consciousness? I have not heard that theory either. Okay, I do have to do some maths now. Okay, I've got to earn my place in on Twitch somehow. Okay, how many solutions does the equation w plus x plus y plus z have equals 100 if w is greater than or equal to 4, x is greater than or equal to 2, y is greater than or equal to 0, and z is greater than or equal to 0? Now, how does this work? Maybe I should do 10. I'll do 10. I'll do 10 as a bit of an introduction to this, bit of a lead into this. I do feel like I don't quite know how to solve that one yet. Okay. So u plus v plus w plus x plus y plus z equals 90. So in that case, we've got 6 symbols. So we can imagine this, right, as like a set, like a multi-set of these 6 symbols. In which case we've got 90 plus 5 dividers, so 95. Choose 5 positions for the dividers, I think. So that's the answer to 10, I believe. For 11, it gets more complicated because we've got 4 symbols. We've got 100 elements in our multi-set. We've got 4 symbols. We need there to be 4 or more W's and 2 or more X's. Now, the way we can imagine this as a multi-set, I suppose, is we could have, like, we're going to start off with 4 W's and 2 X's, right? And then we have 1, 2, 3, 4, 5, 6. We've got 94 remaining elements to fill. Hope you're enjoying the pigeons, everyone. So we've got 94 remaining kind of slots. And we want to divide them between W, X, Y, and Z. So it's going to be, I think it's then going to be 94 plus the number of slots. That's going to, so plus the number of dividers. Now that's going to be 3. So that's going to be 97. Choose 3, I think. So I think that ends up being the answer. I think that's true. Yeah. Okay. Right. Now for, let's do 12 just to check myself on this. Now for 12, how many integer solutions does the equation, same equation, have if it's 7 or more W's, 0 or more X's, 5 or more Y's, and 4 or more Z's. Now here we ended up taking off 6. And we took off 6 because, and that's the sum of 4 and 2. So the relationship is we need to sum up all those numbers, right? So we've got 7, 5, and 4. That's 9 plus 7, that's 16. So we've got 16 spaces chosen already. And then we need to choose as a result 84. Trying to get better at my mental maths here. 100 minus 16 is 84. Okay, so we have 84 more symbols to choose. They can be one of 4 symbols. So we've got 3 dividers. And that means we've got to have 84 plus 3, which is 87. Choose 3. Different solutions, I think. Okay. Now 13. How many length 6 lists can be made from the symbols A, B, C, D, E, F, and G if repetition is allowed and the list is in alphabetical order? Is the list being in alphabetical order? Yeah, this is good for us because we've not been asked about multisets, right? So if it wasn't in alphabetical order, we would have to calculate the permutations of the multiset. But we don't have to do that here. So we're being asked how many multisets of length of cardinality 6 can be made from the symbols A through G. Yeah, okay, fine. So I think in that case, we've got six slots. No, six items plus 7 categories. Minus 1 is 6. So we've got 12 slots in which we put our stars and bars. And then we need to choose 6 slots. 6 dividers, sorry. don't think there's any funny business there. Now 14. How many permutations are there of the letters in the word peppermint? So this also comes up elsewhere in this. Yeah, suppose a multiset A has n elements with the multiplicities p1, etc. Then the total number of permutations of A is factorial over the factorial of the multiplicities multiplied. Holy Hub, I do not unfortunately have a Discord. It's this is the only space so far. I'll take it as a vote for a Discord though. Okay, 14. Right, so in peppermint we've got P. Sorry, need to categorize these. PE, P, P, E, R, M, N, I, T. Why did I do that in a different order? Yeah. R, M, I, N, T. Okay, so we've got 3 P's, 1 E, no, sorry, 2 E's, and everything else is 1. 1 factorial is just 1, so we don't need that in our calculation. Let's keep them there just for now. And so the formula is n. Now I guess n is the number of elements. Yeah. Yep, so n's the number of elements. So we've got 3 plus 2, that's 5, 6, 7, 8, 9, 10. So it's 10 factorial over, come on, over 3 factorial, 2 factorial. I feel like the church bells are going to come back at some point soon. Anyone else getting that feeling? Actually, no, I think we've got like half an hour. I'm way off. Okay. 10 factorial over 3 factorial times 2 factorial. Now that is allegedly 302,400. Now, does that seem right? Seems like quite a few. Kind of makes sense though. Okay. Only high pass. I checked out your website. Will I be able to understand how computer works following it? Just my website? Oh, which website do you mean? I have a few. If you're talking about the Odes website, probably you're talking about that. I would say, so the website, so I used to have a subscription there. The subscription is not active anymore. Almost all the content that is on the website is on my YouTube channel. There are some extras on the website, but I would suggest YouTube channel first. If you really, really want more, send me an email, and I can hook you up. But yeah, so yeah, I need to release more videos. But the objective of the videos is to try to help people who want to engage with computing as not just as a way to get work done, to give us some stuff to do, really. So engage with some interesting topics, do practical exercises in which you figure out more about this topic of computing. And this will involve learning a bit about how the computer works. Yeah. Thank you, Tears of Proletariat. I appreciate those kind words. When you say theoretical stuff, Harmony Hype, do you mean like theory of computing, or do you mean low-level computing? I try to sort of focus on both, but no, in fact, I try and focus on both. Yeah. I too spent a lot of time yearning for more theory. That's one of the issues. I guess it's actually like we're living kind of an exciting time because there is no, there used to be, we wrote a lot of code and the code was kind of all did the same thing, right? We were building products, most of us, but a lot of that work doesn't need to be done anymore. Not in the same way anyway. So in theory, we can focus more on the theory. Yeah, Harmony Pipe. Give some of the videos on my YouTube channel a go, and see what you think. I won't. I'm always tempted to criticize my own work, but I won't. I think probably. I think my best little series was probably on regular expressions. So maybe those few as a series would be kind of good. Yeah, regular expressions are quite closely related to theory of computing, and there's a little bit of assembly in there, I think, maybe as well. Yeah, I think there is actually. Wild. Anyway, do I know David Deutsch? No, I do not. And Kiskala says that you saw I referenced the definitive guide to the Win32 API. How much Win32 did I do, and did you try Handmade Hero? If I did, I don't remember doing so, or I didn't, as I know almost nothing about the definitive guide to the Win32 API, and I've never done any Win32 programming. But feel free to tell me where I may have referenced it. I do sometimes do things I forget about. Okay, permutations in the letters of the word Tennessee. Well, it's got 1, 2, 3, 4, 5, 6, 9 letters. Oh, it was the BMP images guide. You're right. Yeah, the bitmap images. Yeah. Wow. No, that was a cool video. I enjoyed making that one. I completely forgot about that one. Yeah. Wow. Yeah, because the bitmap image format comes out of that. Yeah, wow. Yeah, I think I referenced it just for that file format. I've never written any Win32 stuff. But wow, yeah, that was a fun video. One of the fun things about that video is the exercise. One of the exercises asks people to write their own bitmap, like image generator, and to use it to construct an image of maybe their own country's flag, or like another country's flag, and it's like naturally scaled in difficulty, because you could do France pretty easy, or you could do like Australia's kind of challenging. I think somebody did Australia. You could do Saudi Arabia. I think is pretty challenging. Yeah, that was a fun video. Okay, 15. How many permutations? Yeah, okay, Tennessee, all right. So what were we on? We were on 9. 9 factorial over, what do we got? We've got two n's. We've got 3 e's. And we've got 2 s's. So it's 2 factorial, 3, well, let's say 2 factorial, 2 factorial, 3 factorial, which is just 2, 2, 3. Okay, now what's that? That is 15,120, allegedly. Now that's sort of interesting, isn't it? Just one letter longer and one duplicate fewer, and we get such a, sorry, one duplicate more, or yeah, one duplicate more, and you get such a huge reduction, unless I've made a mistake. Am I sure on the number of e's? No. No, I've missed one. There's 3 e's. Yeah, sorry. Okay, let's try that again. Three 780. Even fewer. I guess there's a kind of, yeah. Oh yeah, true. Yeah, Bubbledon's pointing out that, of course, there's an order of magnitude difference between 10 factorial and 9 factorial. So kind of makes sense. Plus we're cutting down a bit more. Okay, 16. As a community in Canada's Northwest Territories is known in the local language as, I have no idea how to pronounce it. How many permutations does this name have? I don't think that one's going to challenge me that much. 17. You roll a dice 6 times in a row. How many possible outcomes are there that have 2 1s, 3 5s, and 1 6? Okay, let's do this one. You roll a dice 6 times in a row. How many possible outcomes are there that have 2 1s, 3 5s, and 1 6? So I'm naturally tempted, I assume this is the wrong approach, but I'm naturally tempted to look at this approach where we've got 6 slots, and then we've got a 1 and a 1 and a 5 and a 6, and we choose the slots. So it ends up being, we got 6 options, then we got 5 options, then we got 4 options, and then we've got 3 options. Now this won't work because we might get I don't know, 2, 2. Or we might get and these are, I assume we're supposed to consider these the same. So if we take this approach here of just picking, we end up duplicating these to or many other results. So I think that's not allowed. So Bobadon, you're saying as in these exercises are you're saying you're thinking that these aren't the same. I guess, is it a little ambiguous? 17? 6 times in a row. Oh, yeah, true. Miscounted the number of, yeah. 2 1s, 3 5s, and 1 6. So actually, I've just misread the question. Like one possible outcome would be 1 1, 5 5 6, and this is 6 different choices. Yeah, and then we've got 5 1 1 5 6, for example. Same number. Of course, all our numbers are populated, so it doesn't matter. So I guess we do inevitably have to handle the order. We care about the order. So we're actually permutating. We're permutating the number, the multiset 1 1 5 5. What am I doing? 5 5 6. That's what we're doing. In which case we want to use the formula from before, which is 6 factorial over 3 factorial, 2 factorial. Now let's work that out. 60. Three, right? Because the multiplicity of 5 is 3, right? Am I wrong? Oh. I see. Okay. So that's my answer there. Let me just do another one of those because... Come on. There we go. Let's do 18 because I'd like to feel a bit more confident in this type of problem. Flip a coin 10 times in a row. How many outcomes have 3 heads and 7 tails? Well, that adds up to 10. So we're looking at 10 factorial over 7 factorial 3 factorial. That's going to be 120. 19. We've got some boxes again. Balls. People are putting balls in boxes again. In how many ways can you place 15 identical balls into 20 different boxes if each box can hold at most one ball? In how many ways can you place 15 identical balls into 20 different boxes if each box can hold at most one ball? Okay. So the issue with this problem, right, is if we're using our stars and bars approach, then there's nothing really to stop us from putting more than one ball or more than one asterisk, more than one star between two bars. So we need some way to account for that. We need some way to control that. Or it could be 20 choose 15. So we could say we could abandon our stars and bars approach and just have like this many 20 different boxes, each of them numbered, etc. And then we choose the numbers that we want to put the balls in which case it would be 20 choose 15 if that approach works. Now with this approach you do get this won't duplicate anything, so that's good. It's not like permutations. It will I don't think order should be a problem. Yeah, I think this is all right. I think that's okay. Let's do 20. You distribute 25 identical pieces of candy among 5 children. In how many ways can this be done? So I think this one works fine with the stars and bars approach. So we've got Bobadon says a box being filled or not is just a bit being 0 or 1. Yeah, that's true. So the another way of doing this question is that so we've got a 20-bit string and we want to flip 15 of those bits to true. How many different ways are we doing that? Okay, distribute 25 pieces of candy among 5 children. So we can frame this question again by saying we've got like child A, and we're going to have a multi-set of child A, many symbols for each piece of candy that child has, I think. In which case we get to say 25 slots plus 4 dividers, 29. Choose 4. I think. How many numbers between 10,000 and 99,999 contain one or more of the digits 3, 4, and 8, but no others? So we're trying to put together sequences like like this. Now we've got to have one or more of each. I assume 1, 3, 1, 4 and 1, 8 at least. Yeah, so I don't think we'd be allowed to have 3, 3, 3, 3, 3. I think this is forbidden. Yeah, it says and, not all. But maybe I'm just reading into that. Yeah, okay. So in which case, now in this case, we care about order, right? Yeah, we care about order because you know, this number is going to be different to this number. So we do care about order. So it's not a straight multiset. We need to be able to permute it. Now, by the multiplication principle, I guess, we should be able to take all of the different multisets that can be made out of those symbols, which will be, so if we just think about the multiset first, we're going to have 5 spaces plus 2 dividers. So that's 7 slots, choose 2. This will get us the number of different like the number of different, no, actually it won't. Because we need to have at least one. So that's not right. We're actually going to have 3, 4, and 8 in every one. We're going to have 2 left over. If we don't care about order here, let's ignore order for a moment. We're going to have 2 left over. And so it's actually going to be 2 slots plus 2 dividers. So that's 4. Choose 2 for the 2 dividers. And this is going to be the number of different multiplicities of these numbers we can have, I think. So 4 choose 2. I should know 4 choose 2, really. That'd be a nice one to know. 4 choose 2 is 6. 4 choose 2 is 6. Now, we then need to take the permutations of the multiset. Now, I'm going to be a little bit careful here because the multiplicities could be different. So to calculate this, we need to have, well, basically 5 for the ends. Now, are they going to be all the same? We're going to end up with, we could have for example, 3 3s, 1 4 and 1 8, in which case the bottom of this fraction division will be 3 factorial. Or we could have 2 3s and 2 4s. I did it again. And 2 4s and 1 8, in which case it would be this. Thanks, BrainZap. So this would be 4, or this would be 6. Looks a little bit complicated. It's feeling a little tricky. I will be excited by your clever solution after I've made my very not clever solution, Bobadon. Okay, so what are the different versions we can have? We could have okay, let me work this. Let me just brute force this. We've got 3, 3, 3, 4, 8. We've got 3, 3, 4, 4, 8. We've got 3, 3, 4, 8, 8. So hope I don't forget any. We've got 3. Oh, I'm definitely going to forget some. 4, 4, 4, 8. We've got 3, 4. Come on. 4, 8, 8. Wow, really laggy for me at the moment. We've got 3, 4, 8, 8, 8. So that's 6 different possibilities. Don't think order doesn't matter, thankfully. I don't think I've missed any here. We've got one with 3 8s, one with 3 4s, one with 3 3s, and then we've got we got this one 3 3 4 4, and we should have one more. Yeah, okay. I think that's okay. In which case we're going to have on the bottom be 3 factorial. We're going to have this is just going to be 6. This is going to be 4. This is going to be 4. This is going to be 6. 4 and 6. So we got kind of an even balance of these two. Now that makes sense because we know that we've got this 6 here as well. So I guess we just do we just work out the permutations of each of these multisets? Maybe that would work. Are we going to be double counting at all? I don't think so. I don't think so. And we're going to be adding them up because they're not, yeah, we're going to be adding them up. Ah, there we go. There's the church bells. Okay, so basically I think what we're going to get out of this is 5 factorial over 6 times 3, which I guess goes up here, plus 3 times 5 factorial over 4, I think. Now, what's that? What's that going to be? Okay, so on the left we've got 360 on the top divided by 6. Now that's 60. And then on the right we've got 3 by 5 factorial over 4. That's 90. $60 plus 90 is 150. So in theory, that's right. Delightful. Very close to how did you do it, Bubbledon? What was your approach? Please try not to use any words I won't understand. Well, I mean, you can, but then I'll just say, "Oh, cool." sounds sick. Okay, while Bubbledon is furiously typing, I will go and inspect the answers. Bubbledon says, the only difference is I didn't list out all the multi-sets. I noticed that it's either a pattern of 221 or 311 digits divided between them. Yeah, that makes sense. .7. 3.8, maybe? 3.8. Nice. Okay, now let's scroll up with my horrendously slow scrolling. It's really bad. I don't know why it takes so long. Need to work on the performance. Whoa, it's bad. Oof. Awful. Okay. Let me get my green pen out. Green for correct. Okay. 286. Nice. Number 2, no answer. Number 3. 7 choose 3. 7 choose 4. Ooh. Is the answer numerically right? Maybe. Well, it's numerically equal to the right answer, but it's not the answer that we've been given here. Okay, let me look closer. In giving your friend 4 coins, you're giving her a 4-element multi-set made from elements 1, 5, 10, and 25. There are 4 plus 4, minus 1, 7, choose 4, 35 such multi-sets. Why do I feel like I've made a horrendous mistake somewhere? Yeah, I do feel like the logic that's been illustrated in the book so far has been that you're choosing the divisions, the dividers, and there'll only be 3 dividers in a star and bar type diagram. Maybe there's a straight shot through. We don't need to think about the stars and the bars or something. Maybe it just works out. Yeah, well, yeah, I guess in this case choosing it's equivalent. Let's see if I am. Let me mark that one correct, and let's see if I come a cropper later on. And luckily, they're always equivalent. I guess that's true. I didn't think about that. So you're saying choosing the location of the stars and choosing the location of the bars is always equivalent? Well, I guess that makes sense. Wow. Can't believe I didn't realize that. Yeah, crazy. Wow, okay. Okay, 256 is the correct answer. Is it the correct working, though? Yeah, roughly. These church bells will stop soon. These church bells will stop soon. Don't worry. Everyone frantically leaving. Okay, 6. Don't get an answer to. 7. 7, 24, choose 20, which should be the same, right? Let me just double check. 24 choose 20 is 10, 6, 2, 6, and 24 choose 4 is, yeah, it's the same. I don't know why have I been doing it the opposite way this whole time? I swear he taught us to do it that way. Oh well. Still works, I guess. Okay, number 9. 33 choose 30. He's always choosing, you're right, he's always choosing stars. I don't believe it. I gotta check it every time. It's the same. It's the same. I just don't want to be off by 1, you know? Hate being off by 1. Okay. 9, 11. 11 is 97. Ooh. 97 choose 3. No, that's 10. Sorry. I'm messing myself up. 97 choose 3. Well, now he's speaking my language. Where is my cursor? Oh my gosh. Losing it. 97 choose 3. Okay, 13. 12 choose 6. 12 choose 6. Don't get an answer for 14. Let's look at 15. 3, 7, 80. Correct. For 17, the answer is 60, which is correct. For 19, for 19, we've got 20 choose 15, which is right. For 21, we've got 150, which is right. Well done to myself and Boblidon for getting the correct answer there. And anyone else who did get the correct answer. Okay, what time are we? We're on 7:30. Okay. We've been on for 2.5 hours. I'm going to take a short break, and when I get back, I'm gonna do the problem from last time. I'm just going to take one approach to it, which I have identified, and then if it doesn't work, I'm gonna stop. I'm gonna just take it away again, and then we'll move on to. Then we're going to move on to the pigeonhole. No, yeah, the pigeonhole principle. A principle very dear to my heart, as it is about pigeons, as I understand it. So I will see you in 3 to 5. 3 to 5. One of the principles of all time. That's true. See you shortly. And with that startling news from the pigeon, we're back. But we're not going to talk about pigeons yet. We're going to talk about this other problem. Now, what on earth was I thinking before? No hints. So now where are my notes? Should have done this while I was on my break. Yeah, okay. All right. Here we are. Let's scroll our way back. Where were we? Here we are. Yeah. This also kind of an annoying one to annoying question to read. Basically, let's load these things up. So fact 3.5 first. They really do. They really do love referring to things by number. Fact 3.5 is if 0 k yeah, if k is between 0 and n inclusive, then n choose k is equal to n factorial over k factorial multiplied by n minus k factorial. This may have a name. It almost certainly does have a name, but I can't remember it. Otherwise, basically, this equals 0. Now, what is the name of this? 3.5. We don't have a name for it. It's just a thing. Okay. Now, what's the other part? Equation 3.3 is this. The pigeons are supporting me today. n plus 1, choose k, is equal to, whoa, n k minus 1, and choose k minus 1 plus n choose k. And the task is use fact 3.5 to derive equation 3.3. Now I've written down. I will say I spent about, I think, probably an hour or more trying to puzzle this through last time, and I did not really, well, I didn't get a solution anyway. And then after the stream, I cried. No, I didn't cry. It wasn't that bad. But I did. I was, it's always interesting when you come up against a problem that you can't do. I think it's very instructive. In some ways, they're the best problems. And so I consulted ChatGPT deep research, not on this problem, but on the problem of not being able to solve problems of this nature. I didn't give it the problem or anything, so it didn't tell me anything about what the solution was. It tried to speculate actually, but it was wrong. And some of the things that I read in its report were useful. I think basically it connected to some other stuff from another book that I have, which is about problem solving, something like that. Basically, when I'm trying to solve these problems, right, I have a novice brain, right? So I'm doing what's called means end. This is educational theory rather than mathematical theory, but I'm doing what's called means end problem solving. So I start at this point, and I've got some sort of goal over here, maybe. So I've got my givens and I've got my goal, and I don't know how to get to the goal. Like somebody with experience would look at a problem like this and they'd be like, oh, okay, well, I've probably got to do this, and then I 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 got to do this, and maybe, like, let's say they still didn't know, they might still go on a few dead ends here, but they probably immediately or relatively quickly have an idea as to how you solve it from start to finish, and that's called forward chaining. That's the approach you get to use when you know what you're talking about. When you don't, you do what's called, so that's called forward chaining. I'm not good enough at maths to be able to do that. I don't have the schemas, as the theory says. So instead, what I have to do is I start with my givens and I make a move, and I'm like, does this seem closer to my goal? Maybe. If so, I start from here and I go, maybe I'll try this. And then is this closer? And then I do this, do some other thing, basically at random or based on some very faulty intuition. I'm like, is this good? Maybe not. Maybe I won't go that direction. Maybe I'll start here again and I'll do this. And maybe I get to here. I'm like, okay, am I closer? I'm kind of getting closer. And maybe at some point I get stuck and I don't have any obvious moves. This move takes me further away. This move takes me further away. This move takes me further away. And I don't know. If I have it in my mind, I don't think to use it the right move at this point. And so I never get there. So I'm at every point, I'm just thinking, am I closer or am I further away? Am I closer or am I further away? And what can I do next? This is the kind of problem solving you use when you don't really know what you're doing. And sometimes very, very smart people don't know what they're doing because they're working on unsolved problems. But also novices use this method of problem solving a lot because we don't have anything better to solve problems with. We only know moves and we have a vague sense of maybe we're getting closer or further away. There are other approaches too in the literature, but those are the main two ones that most people use without knowing it, of course. So the LLM speculated. This is my reading of what the LLM speculated, that I either probably had some. Maybe I think it speculated maybe notation was the problem. I was like overwhelmed. That would be more of cognitive load theory style of analysis, but I don't think I was overwhelmed by any notation. The notation I'm fairly comfortable with. But basically, I think the thing which jumped out to me is that I couldn't generate the correct, like, sensible moves from the positions I was in. I was sort of, and you can see this if you look back at the last stream. If anyone's watching this as a kind of educational project on on education, you'll be able to see me. I go to some point and I try this, and I'm like, oh, I don't know about that. Is that good? I backtrack. I'm like, maybe this? Is this good? No, I don't feel any closer. Is this? I don't feel any closer. And I sort of like bumbled around. So either my ability to tell whether I'm getting closer is wrong or not fully developed yet, or I don't know the right moves and I haven't tried them. And I think I just wasn't generating the correct moves. So yeah, I need to find a way to generate the correct moves. And I think I did, basically. I think, well, I've got an approach anyway. My approach is convert the right-hand sides to fractions is what I've written down. Hello, Anna Kleinbottle, how are you doing? Good to see you. Yeah, convert the right-hand side to fractions. So in this case, we're looking at this. And then cross multiply to add is what I've written down. Basically, we want to add the fractions together. And then I've written down get the formula on the left. So we want to get this, but for n plus 1, I think. Draw the rest of the owl, you know. So we're going to try that. So we now need to do a bunch of work, basically. So we're going to... Now, my hunch, basically, from all this is that all of this simplifies out and we get the thing we want on the left. That's my hope. It might not happen that way. Now, one also interesting thing that I went through while doing this process was I did a lot of symbol manipulation in my head, which is not something I could do with things like this before, which is always cool to be able to notice your brain able to process these things to the point where you can just think about them while you're doing the washing up, which is kind of, yeah, it's just a rewarding thing about learning. Anyway, so let's move through this. So first, let's actually focus on the right-hand side. So in this case, we're going to have, we're going to have, I'm going to actually make this special. We're going to have what are we doing again? Let me do this properly. Okay, we're going to have n plus 1 factorial. And we're going to then have k factorial n minus, sorry. This is then going to be n plus 1 minus k factorial. And we can remove these brackets. And then I think we can also rearrange this a little bit. I have a hunch this will be useful to rearrange this. So I think what we can do then is change this to n minus k plus 1. I think that's right. Sorry, I'm going a bit slow. Just trying to make sure I don't make any obvious errors. Okay. Plus 1. All right, so this is going to be our goal. That's what we want to end up with. Then let's focus on this part. Now, for this, we're going to have simpler on the top, n factorial. Then we're going to have k minus 1 factorial multiplied by n minus k brackets k minus 1 factorial. And we can then simplify this a little bit by saying this is going to be n minus k plus 1. So this is the thing I noticed as I was working through it. Oh yeah, sorry. There we go. Plus 1. This is the thing I noticed when I was sort of manipulating the all this stuff in my head. And I was like, huh, kind of works out to be the same, right? Which is kind of cool. And may come in useful later. So much of this, by the way, is as a maths novice, you never really know how much of the hints you pick up on in a maths solution are down to what the instructor has placed there in order to help you solve the problem, and how much will just be the natural elegance of mathematics, which will persist. So it could be in the real world, if you're doing real mathematics, none of the things you notice like this will ever be useful to you. I don't know yet. I'm about to find out. Or maybe I'll never find out. Okay. So that's this part. Now let's also add in we're going to add in just n and k. So this will be the normal part. K exclam n minus k exclam as well. Getting some great conversation on this one. The feeling is that noticing sort of correspondences is actually useful in real mathematics. If the check 94 says, if the definitions are well posed, a lot of the proof techniques will present themselves really, really nicely. Interesting. Okay. Right. So the next thing we do is we do that. So this is the move that I didn't think of doing, which I did think of doing later on, which is you just add the fractions together. I think in my mind, I was just like, That seems like a lot of work, and I don't see how it will obviously help me at all. It did occur to me you could just calculate this, but I didn't do it. So that was a move I avoided, but I'm gonna not avoid it now. Now I did have to. I know the basics of how you do this, but basically, if you want to add fractions together, you. Let's say we've got numerator 1, numerator 2. Oops, that's the wrong one. It's the denominator because it denominates, right? Okay, so you then have to end up with d1 plus d2. No, wait. It is n2 d1 plus n1 d2 over n1 n2. Wait, is it really? I'm just messed up the numbers. Oh yeah, I guess my whole thing was wrong. The denominator is on the bottom. I guess it doesn't, it doesn't matter in this case, but okay. So this should be n, this should be d. It denominates, which means it's on the bottom. It's bottoming its way to the top, let's say. Okay. Well, anyway. Yeah, true. So we then have to do a bunch of work. It's topping from the bottom, indeed. Okay. So right, concentrate. So this is this. Let me just put a little thing here when I've done this. Okay, so I've put this in. Now I put n factorial in. Then it's all of this horrendous stuff. It's going to be k minus 1. You can see why I didn't want to do this, right? N minus k plus 1 n factorial over, oh gosh, this is going to be a long line. I can't draw straight lines. Thank you, in a climb bottle. I have in my mind we might need to, simplify that out at some point. And then the bottom sides as well. I don't know why I did this. Don't need it. Okay, so then we have k minus 1 bang n minus k plus 1 bang k bang k minus 1 indeed. And then n minus k bang. Okay, So we've got all of this horrendousness. Now, in theory, we simplify this. Easy. Simple as that. So we've got a whole bunch of choices here, right? We could extract this. Let me actually change my color. There we go. We could extract this. I don't think it probably helps us that much. We could use intercline bottles. Simplification there. Now that would allow us to cancel out the K, right? Cancel out the K. Yeah. So yeah, so then we could say, we could replace this with that. Now if we do that, we can then cancel this, this. Oh, too far. And this. Already paying dividends, indeed. Yeah. So then, yeah, we get to cancel that out, and we still have a K here. And it's not a K factorial, it's just a K. Don't think I've made any errors so far. But let me write down the step just in case I need to backtrack. So we're going to end up with K, N minus K. I need to remember that this is factorial. Ugh. I can probably just remember that. N factorial plus now we'll need the bracket there. N minus K plus 1 factorial N factorial. All of this. Whoa, okay. All of this over the pigeons are rooting for me. Whoa, okay. Getting a bit of lag here on my input device. Right, so we've now got this. So what can we do next? Well, we could take out K minus 1. No, we could take out there's something we could do with this and this. Don't know if it helps us much. We're going to need to get rid of all the K's on top. I can already hear the chat messages on that. And we're trying to work towards n plus 1, right? So... Oh yeah, we've got these two. Oh, okay, that's not that's a bit rash. We've got this, which can be cancelled with this. Right. But then don't we need to cancel on both sides of the addition? So yeah, so we will need then to try to make these two parts the same, which in theory we should be able to do, right? Because this is, these two here, these are just one apart. We know that because we've got this plus one here. So in theory we can make them the same, just what's the right way to do it? Well, we could divide by... We could divide by something, or we could change the right-hand one and the one on the bottom, maybe. Yeah, that would work, right? Then we could transform... we could say... n minus k plus 1 factorial is equal to n minus k plus 1 n minus k factorial. I don't know why I missed the one there. Yeah, indeed. And then if we did that up here and down here, we would end up being able to cancel this and part of this. Wow, I really don't want to do this manually, but I'm going to. Come on, little thing. There we go. Okay, back to the hard work. Now, yeah, so k n minus k. If I invented copy and paste in this little whiteboard, that would be pretty convenient, right? I should invent that. Plus n minus k. Just an honest day's job in the algebra mind, says Wobbledon. That's true. Yeah. A day could be right. Okay. This times n minus k factorial n factorial. Then we get a big line. Then we have n minus k plus 1 n minus k factorial k factorial. And well, we've got 2n minus k's. I guess we don't need to do the other one. Yeah, I just guess we don't need 2, do we? So I guess we can just keep the first one. Any reason not to do that? Well, maybe because I've written it already. Hmm. Yeah, I guess there is a reason to keep that first one there. Yeah. Okay. Let's keep that. Right, now we can do some cancelling. We can cancel this with this with this. Okay. What do we get then? Let's take a look. We get k n, I'll put the brackets there just to be sure, plus n minus k plus 1 n factorial, and then, well, that was a pretty good line. N minus, n minus k plus 1 factorial k factorial. Okay. All right. I think it's we're getting there. We're getting close. Now we can cancel out this term. We can get rid of, no, we can't. We can't get rid of that term. Because it needs to be on both sides of the addition. This could be a moment to extract this maybe. If we did that, what would we get? And then we get to get rid of this. Which then gives us n factorial n minus, no, wait. Plus 1. What are we trying to get to again? Oh, I see. And then we can make this n plus 1 factorial, right? Because n factorial multiplied by n plus 1 factorial. Sorry, it's going to n factorial multiplied by n plus 1 is going to be n plus 1 factorial, right? So this top part gets reduced. So let's write this out again. On the top we've got n plus 1 factorial over, what are we supposed to be getting to again? I guess it's just that at this point. n minus k plus 1, k factorial. Just rearrange that and we get that. Got to make it beautiful after all this work. Okay. Oh. I hope that's the correct answer. We'll never know about Richard Hammack's correct answer, his own, because it's an even number question, so we don't get to know. So chat gets to decide. Looks like chat has decided it's okay. Thank you for the congratulations in a Klein bottle, Max Sylvester Bubbledon. This is a long algebra exercise, so you probably didn't want to write it out. True. True. Check 94 says, this would have been a little faster if you took the common factor before adding the fractions. As in at this stage? Is that what you mean? I didn't know you could take common factors out of expressions like this. I guess there's no reason you couldn't, because we know they're going to cancel out anyway, right? So there's no reason we couldn't take the common factor out of it before doing the addition. I see. Okay, interesting. Yeah. Yeah, true. Yeah. Yeah, just not in my intuition. Interesting. Interesting. All right, well. There we go. Bubbledon says, what I like about this exercise is that you get a completely unambiguous algebraic derivation of the formula, but doesn't tell you anything about the underlying intuition about sets. Why do you like that? Sounds like a bad thing. What? Why do you like it? I mean, it's not necessarily a bad thing. Just I suppose it's a neutral thing. Okay. All right. Well, I will unhighlight this question now. We've still got more of those to do, but not right now. Babylon says, I like it because it's illustrative. Happens a lot in math. You have these two different kinds of strategies. Yeah, interesting. And in a Kleinbot says, yeah, this kind of combinatorics is terrible for intuition, like a bunch of equations that involve the Mobius functions too. Yeah, I guess that's true. I guess that is a thing about mathematics that I've read, which is that sometimes you need to, rely on intuition or leverage intuition, and sometimes you just need to forget intuition and just do your job as a mathematician and calculate things. Do the work. The answer is really do the work or don't do the work. Those are your two strategies. Okay. Right. Now, let's get rid of that, and we'll read this. And do we have loads of exercises on this one? We have a few, relatively few. Let's see. These are some concepts that I definitely have not learned already, or I'm pretty sure I haven't anyway. But after I've read chat. Chit94 says, that shows you can look at the whole thing from a purely algebraic perspective and from a combinatorial perspective separately. A lot of things have several non-obvious perspectives from which to look at it. Finding those helps a lot in understanding it. People dropping wisdom in the chat today. Inner Kleinbot says, my PhD supervisor always talked about temporary axioms for theorems where you could understand the proof but didn't understand the intuition as to why they work. Interesting. Okay. The division and pigeonhole principles. One final counting principle is called the division principle. Before discussing it, we need some notation. Given a number x, its floor, okay, we've got, I suppose it, we're going to draw this like, I don't know why I did it like that. We do that again. Okay, one more time. Something like that. Its floor x is x rounded down to the nearest integer. Okay, fair enough. Thus, 10 over 4 floored is 2, and 9.31 floored is 9, and 7 floored is 7, etc. The ceiling of x denoted, okay, we got the same thing but with the little roof over it. Is x rounded up to the nearest integer, etc. The division principle is often illustrated by a simple situation involving pigeons. Always good. Imagine n pigeons that live in k pigeonholes or boxes. Possibly n is not equal to k. At night, all the pigeons fly into the boxes. When this happens, some of the k boxes may contain more than one pigeon, and some may be empty. But no matter what, the average number of pigeons per box is n over k. Obviously, at least one of the boxes contains n over k or more pigeons, because not all of the boxes can contain fewer than the average number of pigeons per box. And because a box must contain a whole number of pigeons, we round up to conclude at least one box contains n over k ceilinged or more pigeons. Similarly, at least one box must contain n over k or fewer pigeons, because not all boxes can contain more than the average number of pigeons per box. Rounding down, at least one box contains n over k floored or fewer pigeons. We call this line of reasoning the division principle, and some texts call it the strong form of the pigeonhole principle. So fact 3.9, division principle. Suppose n objects are placed into k boxes. Then at least one box contains n over k ceilinged or more objects, and at least one box contains n over k or fewer objects. This has a useful variant. If n is greater than k, then n over k is greater than 1. Okay. Yeah, that makes sense. So n over k ceilinged is greater than 1, and this means some box contains more than one object. On the other hand, if n is less than k, then n over k is less than 1, and so the floor of n over k is less than 1, meaning at least one box is empty. Thus, the division principle yields the following consequence called the pigeonhole principle. Suppose n objects are placed into k boxes. If n is greater than k, then at least one box contains more than one object. If n is less than k, then at least one box is empty. Okay. The pigeonhole principle is named for the scenario in which n pigeons fly into k pigeonholes or boxes. If there are more pigeons than boxes, then some box gets more than one pigeon. And if there are fewer pigeons than boxes, then there must be at least one empty box. Like the multiplication, addition, and subtraction principles, the division and pigeonhole principles are intuitive and obvious, but they can prove things that are not obvious. The challenge is seeing where and how to apply them. Our examples will start simple and get progressively more complex. For an extremely simple application, note that in any group of 13 people, at least 2 of them were born on the same month. Although this is obvious, it really does follow from the pigeonhole principle. Think of the 13 people as objects and put each person in the box that is his birth month. As there are more people than boxes or months, at least one box or month has 2 or more people in it, meaning at least 2 of the 13 people were born in the same month. Further, for any group of 100 people, the division principle says that there is a month in which 100 over 12, because it's 100 people over 12 months, in which 9 or more of the people were born. It also guarantees a month in which 8 or fewer of the people were born. 100 over 12 again. Okay, another example. Pick 6 different integers between 0 and 9 inclusive. Show that 2 of them must add up to 9. Okay, so just thinking this one through, we've got 6 integers. And they can be the digits 0 through 9, which is 10 possible digits. And the ones that add up to 9 would be 1 and 9, 2 and 8, 3 and 7, 4 and 6, and they're going to be different, so that's it. I don't immediately see how to solve this. For example, suppose you picked 0, 1, 3, 5 and 7 and 8. Then 1 plus 8 is 9. If you pick, 4 plus 5 is 9. The problem asks us to show that this happens no matter how we pick the numbers. Okay. So the solution, pick 6 numbers between 0 and 9. Here's why 2 of them sum to 9. Imagine 5 boxes, each marked with 2 numbers as shown below. Each box is labelled so that the 2 numbers written on it sum to 9. Okay, so we've got 5 boxes there. Right. For each number that was picked, put it in the box having that number written on it. For example, if we picked 7, it goes into the box labelled 27. The number 2 if picked would go in that box too. In this way, we place the 6 chosen numbers in 5 boxes. I guess this works because... Oh yeah, I can't add up to 9. Obviously I can't add up to 9, can I? That'd be easier if I could. 0 and 9, 1 and 8, 2 and 7, 3 and 6, 4 and 5. Now if I'd done this properly, I would have probably noticed, or possibly noticed, that all the numbers are represented. All the digits are represented. Which maybe it makes it more obvious to see how we can apply this. For each number that was picked, put it in the box having that number written on it. Yeah, okay, yeah. In this way, we place the 6 chosen numbers in 5 boxes. As there are more numbers than boxes, the pigeonhole principle says that some box has to have more than one, hence 2 of the picked numbers in it. Those 2 numbers sum to 9. Okay. Notice that if we picked only 5 numbers from 0 to 9, then it's possible that no 2 sum to 9. We could be unlucky and pick 0, 1, 2, 3, 4, but the pigeonhole principle ensures that if 6 are picked, then 2 do sum to 9. Okay, let's see if I can do better at this one. A store has a gumball machine containing a large number of red, green, blue, and white gumballs. You get one gumball for each nickel you put in the machine. The store offers the following deal. You agree to buy some number of gumballs, and if 13 or more of them have the same color, you get $5. What is the fewest number of gumballs you need to buy to be 100% certain that you will make money on the deal? Okay, interesting. So the win condition is 13 or more of them. 13 or more of them have the same color. There's no bound on them. Yeah, so let's... I did have this idea briefly before I looked down, but let's... we end up with like boxes, right? For red, green, blue, and white. Terrible, terrible. Yeah, you get it. Red, green, blue, and white. You get one gumball for each nickel. And we need to ensure that 13... Basically, we've got 4 containers. And we have X gumballs bought. And we want to get this so that... I guess this is probably a ceiling, maybe? This is equal to or 13. And we need to work out X, right? Probably. So, just guessing basically. If this was 13 times 4 on the top, divided by 4 would be 13, 11, 12. Okay. So 12 times 4 is 48. So 48 over 4 is 12. 49 is 12.25, which would then solve this. So if we bought 49 gumballs, then we'd be guaranteed maybe Maybe. Let's find out. Let n be the number of gumballs that you buy. Imagine sorting your gumballs, your n gumballs. Oh, okay. Oh, okay, here we go. Imagine sorting n gumballs into 4 boxes labeled red, green, blue, and white. That is red. Yeah. It's the things he chooses to explain are quite funny sometimes. The division principle says that one box contains n over 4. Oh, okay. Can't use my computer today. Or more gumballs, provided this is greater than or equal to 13. You will know you have 13 gumballs of the same color. This happens if n over 4 is greater than 12, so the ceiling of n over 4 rounds to a larger value than 12. Therefore, you need n is greater than 4 by 12, 48, so if n equals 49, you know you've got at least 13. Great, so the answer is like, you multiply that by whatever a nickel is worth. Note that if you bought just 48 gumballs, you might win, but there is a chance you get 12 of each color and miss out on the $5. And if you bought more than 49, you'd still get the $5, but you would have spent more nickels. Explicitly mentioning the boxes in the above solution is not necessary. Some people prefer to draw a conclusion based on averaging alone. They might solve the problem by letting n be the number of gumballs bought, so that n is equal to r plus g plus beta plus w, where r is the number. Yeah, we get the idea. Then the average number of gumballs of a particular color is that, adding them all together over 4 equals n over 4. We need this to be greater than 12 to ensure 13 of the same color, and the smallest number that does that job is n equals 49. This is still the division principle in a pure form. So I don't really get what's going on here. Now, based on averaging alone, they might solve this problem by letting n be the number of gumballs bought. Yeah. Then the average number of gumballs of a particular color is this. We need this to be greater than 12 to ensure 13 of the same color. And the smallest number that does that job is n equals 49. I guess that's fine. Okay, another example. 9 points are randomly placed on the right triangle shown below. Show that 3 of these points form a triangle whose area is 1 over 8 square units or less. We allow triangles with 0 area, in which case the 3 points lie on a line. 9 points are randomly placed on the right triangle shown below. Show that 3 of these points form a triangle whose area is 1/8 of the square unit or less. Okay, wow. Divide the triangle into 4 smaller triangles, as indicated by the dashed lines below. Each of these 4 triangles has an area of half BH. BH is something. H maybe is hypotenuse, maybe? I don't know. Probably something triangle related. equals 1/2, 1/2, 1/2. Yeah, okay, so it's like hypotenuse and I guess bordering something, some length. Some length. Yeah, we calculate the area of those triangles, 1/8 square units. Think of the smaller triangles as boxes, so we have placed 9 points in 4 boxes. If one of the 9 points happens to be on a dashed line, say it belongs to the box below or to its left. Okay, fine. Have to say that to make it work. The division principle says one of these boxes has at least 9/4 ceilinged equals 3 of the points in it. Those 3 points form a triangle whose area is no larger than the area of the box that it is in. Thus, these 3 points form a triangle whose area is 1/8 or less. Okay, so the basic idea here is that we are breaking up this space into some smaller spaces, so some boxes, some pigeonholes. We got this, this, and this. So that's 4 boxes. And then, so and then we know that there's going to be 3, like the pigeonhole principle tells us that there's going to be 3 in one of these boxes. And then we happen to know some principle that indicates that oh no, wait, each of these 4 triangles has an area of 1/8. Okay, fine. Yeah, because this has half a unit of area because it's a triangle of a square. It's a right angle triangle. And then we break it up, and as a result of it being into these 4 equal sections, these have to be 1/4 of the total area, which is an eighth of a unit. And since we know there will be 3 points in one of these by the pigeonhole principle, we can then say that we have a triangle in here and that its area must be at max the area of this triangle. Okay, interesting. People in the chat are liking the triangle exercise. Okay. Now, are these going to be horrible? Because there's only 6 of them. So I have a hunch they could be horrible. Still, I think we persist. Let's see how my brain deals with this. Show that if 6 integers are chosen at random, then at least 2 of them will have the same remainder when divided by 5. So I guess the game here is working out what the boxes are going to be. And the boxes here are going to be, I don't want to draw any more boxes, so they're going to be this. Well, let's say just repeats 1, 2, 3, 4, and we don't get 5 because it's, modulo, whatever. Okay, so we've got 5 groups, And we're going to have 6 integers. So by that logic, then we want a floor because it's an at least. So it's going to be 6 over 5. It's going to be 1. So that's that. That's that shown to some extent. Consider my spoken words also part of the showing. You deal a pile of cards face down from a standard 52 card deck. What is the least number of cards the pile must have before you can be assured that it contains at least 5 cards of the same suit? So we've got like 4 groups here. Can I remember how to draw these just for fun? I think that's that. There's a heart. Fairly sure there's a heart. There's a diamond. And then there's this thing, which I think looks like that. Clubs. Clubs like a clover leaf. True. What was your what was the cool application of the birthday paradox you came across in a climb bottle? What is the least number of cards the pile must have before you can be assured that it contains at least 5 cards of the same suit? Okay, so it's going to be something n over not 5, 4 flawed. Let's say it's equal to 5. So that's going to be, so 20 over 4 is equal to 5, but 15 over 4, or 16 over 4 is equal to 4, famously. So it's got to be 17, right? My clubs look like a beautiful palm tree. This could be true, actually. That's 2. Terrible, terrible. My normal club is way better. Gonna need some color to better work this. Okay. Something like this. We don't have a brown. They can be red. Hear those pigeons fly. In a climb bot says, they use it for reducing the number of port scans required to find an opening in the firewall when a packet leaves. Huh. I guess that would make sense. Cool. That's cool. Do drop the link in the chat if you have it handy. No pressure though. Egmo says, I made a simple image loader as a side project to learn image encodings. Found your vid and reference for bitmap image format. It helped so much. Wanted to say thank you. Extremely well done. Thank you. I appreciate your saying that. That's very nice. I was actually, it came up earlier. I was saying that I really enjoyed making that video and also seeing the results of everyone's work on it. Yeah, that was a fun video to make. Images are always fun to deal with. And I had quite a bit of fun also digging up old Windows, like Windows 9X bitmap images to test my reader with, which is also definitely worth doing if you're making a bitmap file reader. Definitely worth digging out some old Windows 9X UI assets, because they're a good challenge. They're obviously they're spec conformant, but sometimes they're a little unusual. What is the fewest number of times you must roll a 6-sided dice before you can be assured that 10 or more of the rolls resulted in the same number? Okay, so we've got 6 groups, right? And so we're looking at x over 6 forward is equal to 10. It is very thematic having the pigeons in here, isn't it? So I think it's 55, this one. Just trial and error. 55 over 6. Flawed. Look at those 5s. Beautiful 5s. I'm getting better at drawing, writing. That's what they call it when it means things. Nope. Select any 5 points on a square whose side length is 1. Okay, it's a geometric problem. Or it's got shapes in it anyway. Select any 5 points on a square. Now that you've lost me already. Square? The hell is that? Here's a fun question for me. What's your favorite user interaction pattern for drawing squares? Because there are so many. You could just click here, drag down here, and then end here, and you end up with this square. Or this rectangle, if you drag it differently. Or you could just click here and click here, squarify, you get that. Or you could just click, drag, and then it will automatically fill out a square based on the distance you chose. You don't have to worry about accidentally making a rectangle. Or, here's one for you. Then what you do is you start here, you drag out here to form a circle. Imagine that's a circle. Then you square the circle, and that's your square. Right? It's probably something like this. How about that? Try that one. That'll be a fun one. Just square the circle. Yeah. Euclid had the great misfortune of being born in a world without computers. You prefer the diagonal drag. Yeah, that's fair. Egmo says, I'm using the OpenGL for rendering, and for GL text image 2D, you can specify BGR. Uh-huh. That's cool. We're surprised it will take in the pixel data as is without with the padding. I don't have to do anything. That's neat. Yeah, because bitmap uses BGR order, right? Rather than RGB, as we might more naturally expect. Seem to remember that. Okay, select any 5 points on a square whose side length is 1 unit. Okay, so it's one unit. 1 unit. Show okay. Any 5 points on a square. Does that mean inside, or does it mean on the lines? I think it surely means on inside. Show that at least 2 of these points are within root 2 over 2 units of each other. So root 2, right, like that must be because we're imagining breaking it up into this type of thing, maybe? Because this would be root 2, right? No, yeah. 1 plus 1, 2, right? All right. Chat? Help? Okay. So if we were to break this into this, every yeah, this might not be enough. Let's say if we did this, we would know that we would know that if we put 5 points in this, then yeah, so as Egmo says, the bitmap format comes with certain additional little features like padding. So if you have a big row, like if you have a 100 by 100 bitmap image file as of the bitmap format, the right way to specify it involves certain padding, which I think pads the rows, maybe. So you might naturally expect that an image renderer wants to receive an unpadded like struct of, I don't know, array, a list of 100,000, 10,000. What's 100 times 100? 10,000. 10,000 pixels. Yeah. Yeah, scan lines, yeah. Yeah, true. CRT. I forgot about CRT. How can we forget about CRT, though, with channels like LGR helping us remember it? There's a video with a CRT monitor on it that has been coming up for me regularly lately. And teletext, true. Okay, brain starting to switch off. Number 4, okay. So we want to show that at least 2 of these points are within that many units of each other. So what would mean that they have to be more than that? more than that. That would mean they'd have to be further than this distance apart. Which would look like them being, I guess, if we were to cut this, square into sandwich slices, 4 sandwich slices, then anything inside the same triangle will have to be, no wait, because you could have, this here and this here, right? Those would be further than this unit away from each other. So that's not right either. Is there a hint in the number of points? 5 points. So we should be dividing this into 4, right? Basically, we can be certain that if we have 5 points, we're going to need to have more than this here. Now, what am I talking about? The hypotenuse is definitely going to be longer than... No, but they're going to be right-angled triangles. Well, they are. They are, obviously. Wow, it'd be great to know any geometry at all to be able to solve this, wouldn't it? Okay. So, in that case, actually what we're dealing with is this is the hypotenuse. So, yeah, so we're going to end up with a triangle like this. Whoa, okay, come on. Here we go. We're going to end up with this. Now, this is going to be 1 unit long. Which means these two are going to be the same size, same length, because they're also equilateral triangles. Or no, they're not. They're isosceles triangles. So we're going to end up with gosh, okay. 1 squared equals something squared 2, let's say a squared, obviously that's nothing, so we get 1/2 and then we get the root of 1/2. Is this anything? Is this anything? Am I way off? The root of 1/2 is the half of the root of 2. Well, that's good to know. Right. Well, let's say chat source on that. So now if these sides are this length long, and this is 2, and this is 1, then we could also, so the thing that's sticking me a little bit here is that obviously you could have a point here and a point here that are further than A away, and we know that, but I guess we could redivide it again, and we could say we've got it into quarters like this. So we've got it into these subsquares. Now these subsquares, the furthest anything can be from anything else in this subsquare is A, which is root 2 over 2, as established by chat. And if we have 5 points on this in this square by the pigeonhole principle, let's say, one of them's going to have to be, or 2 of them will have to be in the same square. So 2 of them will have to be within A, and A is this. Okay. All right. Let's hope I don't have to do that again. Thank you, chat, for your assistance on that one. Prove that any set of 7 distinct natural numbers contains a pair of numbers whose sum or difference is a multiple of 10. Why I always do the difficult ones at the end. Prove that, well, I don't know how to prove anything for starters, but let's say we can just indicate that any set of 7 distinct natural numbers being like 1 onwards in integers, non-negative, non-zero integers, contains a pair of numbers whose sum or difference is a multiple of 10. I suppose in that case, we only care about the final digit. So let's say it's the same. This set of 7 natural numbers is the same as choosing 7 distinct natural numbers, seven of the digits 0 through 9. Is that right? Well, yeah. I'm not certain that's true. It seems true. Let's try some out. When we say multiple of 10, we're talking about something that ends in a 0, right? Let's just pick them. Let's pick them. Let's pick them and find out. I'm using my free will here. Okay, now I've got 7. Now the sum. These two sum up. We only need to look at the last digits to work out that the sum will be a multiple of 10. Because we can see 3 and 7 there. We know that these won't sum to a multiple of 10 because it won't end in a 0. However, let's say if we wanted to subtract. Are there any here that subtract? They don't need to be. Well, these two do. So we can tell those two do because they end in a 1. What's another set of 2? Let's say we had 100 or 1010. Those are the same. Let's say we had 1001. The only thing that could get us a difference there would be 1. If we had... The only thing that could make this... Well, actually... No, I think it's... Don't they have to be they have to be the same end digit, maybe? Is there any counterexample? With subtraction? Okay, so let's take that to be true. If final digits are identical, difference. Terrible. Difference is multiple of 10. Okay, so if they're identical, the difference is a multiple of 10. And if the final digits sum to 10, start to stutter. Does happen from time to time. Okay, so in that case we've got the box where both are the same. And we've got the box where, well, I guess we have to have 6 as well, and 7. And this number I've heard of called 8. And then 9, of course, as well. Can't forget 9. So we've got this. This is like one category. We don't really care about any others necessarily. Maybe we do. And then we've got, we don't have that. Then we've got 1 and 9, 2 and 8, 7 and 3. I'm just losing that. 6 and 4. I should really align these better. 7, 3. No, what am I doing? Come on. That's it. 5 and 5, I guess, but we've already got that box here. Chat has realized what's going on in the problem. Chat has some notions, I believe. Any set of 7 distinct natural numbers. So we're probably looking for something of the form so messy. 2. So we want probably or actually no, it's not. It'll be something. I'm not necessarily certain it'll be this. But we do want to be able to group these somehow. We're grouping them probably by last digit. So let's say we're going to have 10 boxes. 0, 1, etc. Now, if we can show this for like differences relatively easily. So if we want to sort of reshape this problem and say that we want to say prove that any set of 11 distinct natural numbers contains a pair of numbers whose difference is a multiple of 10, we can do that because we'll know that of these 10 boxes, we'll have to have one duplicate in there, and so we can subtract. We will have one of these basically. So the difference part for a larger number is easier. Then we saw one earlier where we put things into one of 5 boxes, but that seems like it would produce too strong a solution. So we could have a box labeled 1 and 9. We could have a box labeled 2 and 8. We could have a box labeled 3. I don't know why I flipped that over. 3 and 7. And we could have 4 and 6. And we could have 5. Then we've got 0 to worry about. guess 0 and 5. But then if they end up being two of the same, it doesn't work. Yeah, because we could have, in this case, we could have 1, 2, 3, 4, 5, 11, 12. And then we get 1 in here. Now, the only way I think we've managed to construct that is by having two of the same final digit, which then enables us to take the difference of these, which means the difference of these will be a multiple of 10. So maybe that's it. Maybe that's the maybe that's why it works. Can we construct something which doesn't work for these categories? So we either need to repeat the final digit. If we repeat the final digit, we lose because we if we repeat the final digit, we can subtract the two numbers. So let's say if we choose 1 and 11, we could subtract these and we get, or we difference them rather, and we get 10. So we can't choose the same one. If we choose a different one, yeah, so let's say we've used up 1, 2, 3, 4, and 5. Now, is there any way we can add one that means we don't have a sum or a difference? If we try 16, we end up with 1 in here. And if you add 4 and 16, you get 20. So that won't work. What about if we don't fill these up and we go $50, let's say. Then can we add another one? We could add 55. Yeah, so that's a problem. If we add 55, we don't get a difference that helps us. And we don't get a, yeah, okay, so 5 and 0 can't go together. So we need a category for numbers ending in 5 and a category for numbers ending in 0. If we do this, we end up with this and this filled. Now we shouldn't be able to add another number without hitting one of these boxes. We've represented all the final digits, so that's definitely obviously true. But can we add one without, obviously this is nothing like proving it, but convincing myself of it anyway. If we add like 99, we lose because we can add 1 and 9 to make something. If we add 64, we can subtract these to get 60. What about anything ending in 0? We lose because we've got 50 here. So if we subtract these two, we get a multiple of 10. We don't have a 9, so what about 11? No, we lose there. Excalib's washed. Welcome. Glad you think it's a cool idea for a series. Yeah, definitely. It's definitely worth doing. Going through the... this isn't the art of computer programming, although it is a prerequisite on the way for me there. But yeah, it's definitely recommended. Do feel free to get the books and follow along. Okay, so we've got 6 categories now, which seems promising. I think, though I would not quite claim to have proven that I think I can see that there are a few steps in the middle here that if I could prove them more rigorously, like for example, this fact and the other one for summing together, like if I sort of had some rigorous language for that, I could prove that. Then I could prove these boxes were sufficient, like all numbers can be grouped to this, and if we have a duplicate in any of these boxes, then we end up having either a difference or a sum. So we've got 6 categories, and we want to say by the pigeonhole principle, if we take the floor of n over 6 and we say that's got to be equal to 2. No, what am I doing? What am I doing? I'm just writing stuff now. Basically, by the principle, if you've got everything has to go into one of these boxes. If we have 6, we can get into exactly 1, but the 7th will push us over into having an extra one in there. Extra one in one of them. If we have a duplicate in any of them, then we have either a difference or a sum who is a multiple of 10. So there you go. Okay, cool. Any thoughts on whether I'm right? I think it's an odd numbered question, so we in theory we get the answer. The proof goes as follows: take any 7 digits, then one of those 7 boxes contains 2 numbers. Either they are in one of the boxes with 2 digits. If the end digit is the same, then subtract to get a multiple of 10. If they're different, add them together. If they end in 5 or 0, then add together to get a multiple of 10. In any case, you end up with a pair that adds or subtracts to a multiple of 10. Okay, so you're kind of like, you kind of start with these boxes, and then you kind of follow some distinct logic for each box. That's kind of an interesting. Yeah, 6 boxes. Yeah, and then you have a different logic for each one. Okay, that makes sense. And then you look at each one depending on which you're in. Okay, that's interesting. Thank you. That's actually an interesting way to think about it. Great. Okay, now let's do 6, and then we'll see what Richard thinks of all this. Given a sphere S, a great circle of S is the intersection of S with a plane through its center. It's not looking good for me here. sphere. That's 3 dimensions, right? Looks like that. Great circle of S is the intersection of S with a plane through its center. So we're going to end up with a kind of, what? Center, let's say. We're going to end up with like, since it's through the center, it should be a circle, right? Yeah. So we're going to end up with a kind of, like a sheet of paper with a circle on it where the sphere has gone through it. Every great circle divides S into 2 parts. A hemisphere is the union of the great circle. Whoa. A hemisphere is the union of the great circle and one of these 2 parts. Right. So that's... we're just adding on an infinitesimal layer onto the half, I guess. Show that if 5 points are placed arbitrarily on S, then there is a hemisphere that connects 4 of them. Egmo says, do you follow Freya Holmer? They do a lot of math and programming stuff that's way above my head. I don't actually, but I will note that down. And next stream I will say more. Thank you for the recommendation. Always good to have recommendations. Five points are placed arbitrarily on S, and there is a hemisphere that contains 4 of them. So we might have like 3-dimensional space. I have no idea how to notate this. Something like that. Let's say they're all inside, of course, and we need to show that there is a. If we divide it into two hemispheres, then there's a hemisphere that contains 4 of them. That seems really counterintuitive, you know. Maybe I do follow Freya Holmer. I was thinking YouTube, but I wasn't thinking Twitch. I think I do actually. No, I think I do. I think I've been on a few of Freya's streams, maybe. Yeah, Freya. I think Freya inspired me to improve my board game. Yeah, no, I think I do actually. Yeah, way above my head as well. Way above my head. Or maybe not. Maybe I'm thinking of someone completely different. Who knows? Who knows? I think I'm following Freya. So I definitely do know about Freya. No, yeah, I recognize the backdrop now. Yeah, all kinds of like, yeah. Basically, I looked at Freya's setup and I was like, wow, that's way better than mine. So I had to make mine better. Okay. Inner Climb Bottle is also saying, is trying to blow my mind even more. There's no formula for the geodesic distance between points on a torus. Wow. Wait, Stephen Wolfram is streaming right now? Is Stephen Wolfram streaming right now? Have we got our raid sorted? we got our Wolfram raid? Okay. All right, now where, I don't even know where to begin with this one other than just think about it. Okay, so I immediately want to construct like a counterexample. Let's say I've got these 5 points. I guess if I put the hemisphere here, like let's say the circle, the sphere is like this, then I could instead put the hemisphere here and then split them, or I could put it here, maybe. So I could be really mean and I could just isolate one of them. I could say, you're out, you suck, go away. Or let's say I've got, does it even need to be in a sphere? I guess another way of thinking about it is, let's say I have any points. I could draw a line to separate them, which could then become the hemisphere of some circle that contains all the points. Which I guess satisfies me somewhat. But I get to choose the sphere in that case. So not as satisfying, but let's say if I construct them differently. So if I try and really space them kind of evenly. Then I could have the kind of equator here, maybe. And then if I try and, game it even further, my headphones are about to die. Doesn't matter though. Apart from the fact that I need to mute the audio. Okay, let me know if there's any audio issues. So if I try and, what was I even doing here? Whoa, okay, that's not right. It's weird. I feel like when I check my headphones out, and all that's on in here is the birds, right? But if I take them out, I feel like I can't hear chat. That's the sensation I'm getting. Like, what? Speak up. I can't hear you. I'm going to miss something. Okay. So if I try and... I could then maybe have this. But this is all just sketches, so I'm not really certain. I guess what we're saying in 2D space is... that there's like a left and a right. Yeah, it is like that. Egmo's saying it's like when you turn the music down in the car when you get close to the destination, so you don't miss your turning or something. Cognition is weird. So the thing which is kind of like I'm a bit of a loss here, because like I could imagine, let's say, if I had like two halves of a sphere, I can definitely show that if you add two, or three rather, you're gonna have to have one in like one of these hemispheres, right? So that's possible. Let's just think about the circle. Yeah. I mean, is it true of a circle as well? Like, not quite. Doesn't seem to be true of a circle. I guess you could, let's say this doesn't seem as true. In fact, what is this? What have I got here? Let's say this was a sphere. How would I divide this? Inner Climbot saying there's a true statement for the circle in a similar vein. For instance, for any 3 points, 2 of them lie in the same semicircle. Yeah, that makes sense. But that's not interesting. Yeah, I guess not. So if there's 2 for this, if it's 3 for the circle, and we've got 5 and 4, we've got 3 and 2 for this, for the circle, and we've got 5 and 4 for the sphere. Oh yeah. Inner Client Bottle said, shortly before solving the problem, seemingly, convinced myself that it's true for 4 points that 3 lie in the same circle. Which I guess makes sense and shows us the... Is that another side of it? So if we had like... Maybe something like this. This makes it particularly difficult, but basically we're looking at like this, right? Okay. I think this is going to be one to puzzle on. I don't think I'm going to solve it today, especially since it's dinner time. But we will look at the answers because we don't get the even number answers, so we don't need to worry about spoilering that. Let's take a look at the answers and see how well I've done. See how poorly I've done, maybe. Come on. Right. Show that if 6 integers are chosen at random. I need to put my birds back in. Can't focus without them. There they are. Show that if 6 integers are chosen at random, at least 2 will have the same remainder when divided by 5. Pick 6 integers at random. Imagine 5 boxes labeled, yeah. Each of the picked integers has a remainder when divided by 5. Yeah, okay, this is the logic I used. Okay, so now for number 3. What is the fewest number of times you must roll a 6-sided dice before you can be assured that 10 or more of the rolls result in the same number? Okay, imagine 6 boxes, label 1 through 6. Every time you roll it, yeah. Yeah. 55, great. Now let's look at 5. The tricky one. One of the tricky ones. Okay, what does he say? Prove that any set of distinct natural numbers contains a pair of numbers whose sum or difference is a multiple of 10. Solution. Let S be any set of 7 natural numbers. This looks promising. We want to show the sum or the difference of 2 of them is a multiple of 10. Take 6 boxes labeled as follows. Notice that if a box has 2 numbers in it, then they add up to 10. Makes sense. Take the numbers from S and put them into the boxes in the following way. For each X in S, look at its rightmost ones digit and put it in the box that has the digit on it. For example, put 2, 5, yeah, I get it. Because S has more elements than there are boxes, at least one box will contain 2 or more numbers. Take 2 numbers X and Y that are in the same box. If their rightmost digits happen to be the same, then the rightmost digit of the difference. Oh great, I've just gone into dark mode. Didn't anticipate streaming this late. Turn that off. Too late. Yeah. If the rightmost digits have to be the same, then the rightmost digit of the difference is, yeah. So this difference is a multiple of 10. On the other hand, if the rightmost digits are different, then because they are in the same box, their rightmost digit sum to 10. Therefore, the rightmost digit of the sum, yeah. Great. Okay. Wow. Sort of. I did that. I'm going to give myself 80% of a mark for that. It was a fun problem anyway. We were really in tune then, chat. We were really in tune. Give everyone a tick for that. Everyone gets a tick in the chat. Well done, everyone. Great answers. And if you got the right answer for number 6, you get a chat. You get a tick for that too. Okay. All right. Now let's yes, one indeed. Let's see who we're all going to go and hang out with. They're saying, was Stephen Wolfram really streaming? He wasn't really, right? Wait, he is? Oh my gosh. Okay. Oh, we're definitely going there. That's wild. All right. Exciting time. Okay. Get ready to experience Stephen Wolfram live and on Twitch. Wow. Okay. Have fun, everyone. Have a great rest of your days, and see you next time.